Now we're going to switch gears. So on the first assignment, on the first 5 days, you talked about frame. So now at this point, your Rust should have improved like 200%. You should know how to build your own blockchains. So congrats for that. And now on the second part, we will talk about XCM, which is basically interoperability, how to send messages from one chain to another. And I think that the hardest thing of this is just Rust and lack of documentation. So your Rust should already be good enough, and I'll teach you everything you need to know. So make sure to ask questions, and you will get it. You will get it. Here we go. Okay. So on this module, we'll see what XCM is, what primitives make up XCMs, so XCM is a sort of DSL language that you can use to express intentions that you want another chain to do. So how those scripts, how those messages are made, what they are made up of, how they are executed. So once you receive an XCM, you will execute it, and some state change will happen because of that. The XCM palette. So XCM is just a plain Rust struct with functionalities, traits, all the things you've seen so far. Has nothing to do with blockchain in a way. Like the core of XCM is just a way of processing instructions. Like it has nothing to do with it. And then we use the XCM palette as the gateway, like from frame to XCM. So we're going to be talking about that. Then how to configure systems to work with XCM. We made a very generic system. As you all know, we like to do that, which complicates things a lot, but really makes things flexible and gives everyone the power to do the chain they want, like they want it. And then how to craft XCMs. So how to build these XCM messages, XCM programs that will be sent around and executed by other chains. So what's the problem? The problem is that Substrate and Frame encourage an ecosystem of many blockchains, but we don't want every chain to have to do everything. So you've seen the Polkadot vision, the multi-chain vision. You've seen Substrate and Frame. So of course, you need a framework to build blockchains if we want there to be a lot of blockchains. But then what if we want those chains to be specialized on something? Like you might have a DeFi chain, a gaming chain, NFTs, whatever you want. Some chains that just have smart contracts, but they are specific to some vertical, like DePIN or so on, decentralized physical infrastructure and so on. So we want them to be able to send, first of all, funds around, tokens around. So if you are on one chain, you can use another chain, and then the off-chain library can just abstract that away and make sure you're dealing with Polkadot. But in the behind the scenes, you're sending tokens around. But also that you're able to execute code from one chain, send a message saying, I want to execute a code on this other chain. That's also important. So yeah, specialization allows chains to focus on their particular value proposition and do it well. That's what we want. And the solution is messaging. Like the solution to this problem is sending some sort of message saying, hey, I want to execute, I want to do something. That's the solution. But how do you do it? You need some sort of transport protocol. You might have heard of bridges at this point. I believe on the fundamentals or on the Polkadot module, some bridges might have been mentioned. But we have this system called like UMP, DMP, which stands for upward message passing, and DMP, downward message passing, which is from the relay to parachains. HRMP, which is horizontally relayed message passing from to parachains. And then we have bridges, which function in a different way, because UMP, DMP, HRMP, they're sort of the same thing. And they use the underlying Polkadot system to send messages. But bridges cannot take advantage of the fact that the chains are within Polkadot security umbrella. So bridges work in a different way, and we have bridges, for example, Snowbridge or Hyperbridge, from Polkadot to Ethereum or from Polkadot to other L2s. And these are trustless bridges. Of course, we have some smart contracts like Wormhole on Moonbeam and all those things as well. So there are various ways you can have transport protocols. They come with different advantages, but yeah, all of them work for sending a message from one place to another. Some of them are more general, and some of them are more specialized. Some of them are trustless, which means no single entity can screw you over. But some of them are trusted as well, and I would encourage to use the trustless ones, depending on your use case, of course. So they don't come in the same size. There's another acronym which you might see floating around, which is XCMP, which is a bad name because XCM and XCMP have nothing to do with each other. We'll talk about, not nothing, but it's a separation of concerns. Like one is application layer, so XCM is application layer, and the message passing is transport layer. If you know about the OSI stack from the internet, that's what we're trying to do with the separation of concerns. HRMP is kind of like XCMP light. XCMP literally stands for like XCM passing, and it is something that's meant to be, it's more, how do you say it? Uses less storage, is more efficient. We still don't have a fully off-chain XCMP done, but you might hear it around. For now, what we use is called HRMP, and that's what you'll see all over the documentation. Okay, so now that we talked a little bit about transport protocols, so we know that this problem of messaging, or the solution of messaging, needs some way to send a message from A to B. Good, but now what message do we actually send? For example, when you're making an off-chain application and you connect it to a chain, you might write an extrinsic, right? You put we learned about this in Frame. You put a pallet index, a call index, then there's some other the parameters. Then you might put a signature and some other data. And that's the message that you want to send to your chain. So why don't we use that, right? Why we don't use something like native transactions? And we have one chain literally submit a transaction on the other chain, or like at least send the bytes, the same bytes as it wants to execute. Probably without a signature because the chain cannot sign anything. But you might be able to send a call maybe, and then you execute the call. That might be one, like the first idea you have, but there are some disadvantages to that. So the format changes from time to time. From system to system, the format changes. So if you are on chain A and want to speak to two different chains, B and C, then you need to basically learn their format. Like you need to look into their palettes, you need to look into their indices and so on, and then you can talk to each one of them. This is not good if you will have like hundreds of blockchains. So is there a better way? We'll see later. And then even within the same system, the format might change because there might be a runtime upgrade. So you are sending messages to another chain and everything is all right, and then they do a runtime upgrade that breaks everything, and now you need to go ahead and fix it. That's also not good. I mean, it's doable, but maybe there's a better way. Then common cross-consensus use cases, the map one-to-one to a single transaction. Like it cross-consensus messaging or cross-chain messaging is quite, it takes a while for the message to arrive. It's not synchronous. So we cannot just expect that we send a lot of transactions and wait for the response and then send another transaction back in order to do what we want. It would be better to be able to send a message that does a bunch of things. And then you can, send a message that, for example, moves some funds from one account to another, does a swap, then executes a smart contract, then does something else, and then comes back to you because you want to reduce the back and forth. So all of that is not in one transaction, and you don't want to create a specific palette with one call for each of these scenarios. So we can do better. And then different consensus systems. Here, caveat, I'm using consensus systems because it could be a chain or a contract. have different assumptions, for example, fee payment. So we also want to transmit the idea of feeless transactions from in different chains, but feeless transactions might work in a different way on different chains. For example, some chains might not allow feeless transactions at all, like Ethereum, and some chains might. So we want to build like a separate fee system on XCM, just so that we can allow for free transaction in some scenarios. And we can do some stuff, we'll see this later, we can do some stuff where we can, if a message comes from a chain, we can make sure it's free. But if it comes from a user, we can make sure they need to pay for it. All those things are very important because some systems might be designed with multiple chains in mind, and they might do partnerships with the teams behind those chains, and they might not want to spend on transaction fees. Good. So there are a lot of disadvantages to this. Of course, the advantage is that it's simpler. You just send some, you already have the calls, you just send that, and the other chain should be able to interpret them. But yeah, disadvantages. So a better solution is a domain-specific language that is agnostic to the underlying chain implementing it. Like, what if we could have a language that is declarative, and we say, hey, please withdraw some funds, separate some of those funds for fees, then do a swap, and then deposit funds somewhere. That sounds good, right? That sounds like a nice message that you might be able to make and send somewhere else. That's the idea. And then it's the job of the recipient to interpret that message. You should be able to express multiple actions in a single message, which is this idea that I told you about. You should be able to write a message that is not just do X, but rather do this, then do something else, and then finish. And it should be flexible enough to accommodate multiple different paradigms, because we don't know with which chains we're interacting. So for example, it should be able to handle EVM chains versus substrate chains. It should be able to handle chains that use one palette versus chains that use a different palette, chains that have changed their whole, maybe they don't use frame, they use substrate and use something else. It should be able to accommodate for all of them. So XCM is a language for communicating intentions between consensus systems. Those are the three basic characteristics of the language. So it's a language in the sense that it has, you write it in a specific way. It's a domain-specific language. We also call it a message format. Whether or not it's a language of a format, it's kind of like, it's very similar. I will go for it being a language, but it's the same. Of course, like XCM, at the end of the day, it gets scale encoded. So kind of like scale encoding is the format. This is the language. And you communicate intentions. You communicate this idea of, hey, please grab some tokens, pay some fees, do a swap, do a deposit, execute smart contract, like really declarative things, intentions that you want the other chain to do. And yeah, between consensus systems is between chains or contracts or anything that exists in consensus, which means anything that has a bunch of nodes, is decentralized. So yeah, so XCM stands for cross-chain. It stands for cross-consensus messaging. You can think about it cross-chain messaging if that's simpler for you. The C works anyway. So the language is a cross-chain DSL. Each message is a script that allows expressing multiple actions. So each message will be a collection of, each message will be a program that will be executable on the other side, and you write it in a way that you code it in a way that when it sends, you know it's going to be executed correctly. Intentions. So blockchains are sovereign entities. So as you've seen, a blockchain can do basically whatever they want. So we want to make sure that they keep on having that sovereignty. So the language only expresses what we want the receiver to do, but it cannot enforce it. Because maybe you send a message to someone in this language that is very general. You send a message to someone saying, hey, please do a swap. But the chain doesn't support swaps. So it's going to have to, even though you want it to do a swap, it cannot do a swap. And maybe you send a message to another chain, and while you want it to do things, maybe they decided to block every message coming from your chain. Because chains are sovereign, we want them to keep that sovereignty. Like, we want them to decide whether they want to receive messages from a particular sender or whether they want to support particular features. So we need this idea of intentions to make sure that you can accommodate for all of these different paradigms. So verification can be done on another layer. So this doesn't mean that it's a fire and forget, and then I'm not sure if anything happened, which is what I've heard some people say. You can check the result with a light client, for example, and sometimes it's the job of the transport protocol to check for state changes, right? So some transport protocols might provide a verification step where they don't only transfer your message from A to B, they also verify that the expected outcome on B happened. And that might be the case with something like HybridBridge, for example, and they verify it with storage proofs, for example. But on the language level, when you're writing the message, you don't need to think about these things. That's the idea of the separation of concerns. And then the last part we talked about is the consensus systems. I'll just briefly mention that, yeah, actors can be smart contracts, and it could be anything that acts like a chain. Like, it might be just one server, but if it acts like a chain, then it can interpret these messages. There's no reason why they couldn't. Good, so that's like what XCM is, like the introduction. It's also versioned. So we do you might be familiar with versioning for message formats or protocols, because some chains might support version 3, some might support version 4. So we have, yeah, different versions where we change stuff. In reality, all versions are backwards compatible. And now we are sort of stable with version 5, and will take a while until we create a new version, and it will be totally backwards compatible to version 5. And there is a way to like subscribe to version changes and make sure that you update your chain to know who speaks what. Like, a chain keeps track. This chain that I know speaks v3, this one speaks v5, and so on. And then what goes in each version is defined via an RFC process. We use the RFCs on the Polkadot Fellowship. It's one of the mandates of the Polkadot Fellowship. If you read the manifesto, is XCM. So we use the RFCs there to discuss over new features, and when we have like a good amount of features, that will go into the next version of XCM, and then someone needs to code it up. Okay, here there was an image, but it's dead. But it's just saying the idea is the title is the important thing, which is XCM versus message passing. So we use XCM to talk about the application layer, so how you write programs, how you write messages that will get executed on the other side. Message passing is the way those messages that you write are sent from A to B. So I know a lot of you, because it has happened all the time, are really interested in knowing how message passing works. I know, but it's very useful to do this separation of concerns and leave message passing for its own thing, and how to actually write these messages and use these messages for now, which is what I'll mostly talk about. So on these days, we will talk about how to use XCM. We will not talk about how the message passing necessarily works. As in your assignment as well, you will just do a little bit of cross-chain communication, and it doesn't matter like where it's coming from, right? Even like locally, you will use like a mocked sort of transport protocol, and that's fine. Good, so I just wanted to mention that. So XCM itself is not a transport protocol. It doesn't care who is the responsible for grabbing a message and sending it from A to B. Just, yeah, I wanted to mention that. There will be confusion, and I know there will be, but it's just a separation of concerns. And then a simple, yeah, terminology thing. So XCM is the format, the language. Stands for cross-consensus messaging. And XCM is a cross-consensus message. We kind of reuse the M to mean from messaging to message. Some people call it an XCM message. At this point, the battle is lost. Most people say it's an XCM message, which would be a cross-chain messaging message, which is kind of annoying, but the battle is lost at this point. You will see all over the code, you'll see XCM message, so don't feel bad if you use it. Yeah, the same way it's not called an ATM machine, which is a, what is it, an auto-transferring machine? Automatic, yeah, automatic tailor machine. And then we can also call them XCM programs, since they're executable. XCM programs is kind of my favorite, because they are programs written in a language, XCM programs. Sometimes I will see just you have an XCM and you say, yeah, a cross-consensus message, and you. Yeah. Good. So that was the summary of the first mini lecture, which is just an introduction. So we changed gears from frame into a whole new thing. So I just wanted to give you an introduction of what the problem is, like why are we even talking about this, what the solution is, and now in following lectures I will share like how this is actually all the primitive ideas that, or fundamental ideas that you would need to know, how this is actually coded up, how this is actually used. And then in the afternoon, we will have exercises, hands-on exercises of actually using it and seeing on your machine that it works and how it works and so on. So here on this mini lecture, we learned what XCM is and why it's useful. Hopefully you got the idea of why this over, for example, native messages. There are other ideas, like maybe you could send an EVM program instead of an XCM program, but each of them have their disadvantages. So we learned what this is, why it's useful, and we learned what transport protocols exist in Polkadot. So if you go into the documentation and you see like DMP, UMP, HRMP, you know that they are a message passing protocol, transport protocol. So questions. And now I'm gonna need some mics. There you go. Yeah.
Like two questions. The first one is related to the XCM standardization.
They can what, sorry?
The standardization, because the way I see XCM is like a way to standardize sending messages between different blockchains. And I can understand, or it makes sense that inside Polkadot ecosystem there is a way of standardization, but when we come like to other like blockchain, how you can manage different standardization, like even in like let's talk about like the Rust-based smart contract. It is in Rust, but each blockchain network has its own standard way of writing smart contract. This is the first question. Second question is related to the verification. I know like when you send a message from the source chain to destination chain, so many protocol, like almost all of them, like give you kind of like a status about your destination chain message, whether it's whether it's successful or not. And I'm wondering how, because one of the challenges I saw so far, like I'm sending my message from source chain to destination chain, and I'm updating my state, for example, like locking tokens, whatever updates I'm making in this source chain, and I'm expecting releasing this token or having kind of like other stuff in the destination chain. There is no way to revert back the changes if my transaction in the destination chain is not successful. Yes, it is committed, it is there, but like it is reverted. So I'm wondering how in Polkadot it is work. Like if I'm sending from parachain to another, or I'm sending from Polkadot from parachain to Ethereum, given that my transaction to the destination chain is reverted, is there a way to revert the updates in my source chain, or the developer has to take care of this part?
Okay, so there were two. The first one was, like, yeah, standardizing outside of Polkadot as well. So XCM just has a format which is specified in a document, and it tells you like what instructions there are, how you put them together, and then what they're supposed to do. And anyone can grab that and implement it in a smart contract, or so implement something that interprets the instructions and does what they need to do in a smart contract. It's really like, it's pretty general, and smart contracts can do so little, so sometimes that might not be the best idea. But the idea of XCM is that you're just transferring, you're just sending intentions, right? So in Polkadot, I see you're grabbing the mic again. I'm not done. But so in Polkadot, you send these intentions. You can send them to different parachains, and that's like happy case, because all the parachains are built with Substrate, with Frame, and we do have an XCM palette, and we do have all our code in Rust, so it just works. Everyone has the same code. But if you're sending to Ethereum, so for example, what Snowbridge does, which is a bridge from Polkadot to Ethereum, is Snowbridge will receive an XCM or an XCM program, and they will see the intention and convert it into one of few commands to send to the Ethereum smart contract. So you can really think of XCM as some sort of expressing intention. You don't need necessarily to execute it in the same way. So in the case of Snowbridge, they just convert the intention into a command. They want a few commands, and then they send that into the Ethereum smart contract, because it's cheaper to know that you can only support, or to know which things you can do. That was the first thing.
Can I follow up here? Just
Yeah, sure.
A tiny like question, like
Yeah,
the level of adoption, because the way I see it is like it depends on the adoption of the community, or like whoever like wants to use the standardization. So how like what is the level of adoption to use XCM and other like blockchain to provide this cross-chain?
Yeah, so like usually on these systems, like so it's kind of like a war between different blockchains, right? Like they should work together. They should have standards between them if they want like their Web3 vision to come to life, right? We're sort of stuck with people vouching for their own token as if it was a football team. So they create their own thing, and they say, my thing is the best thing. And what we can do is just struggle to join these isolated islands with bridges and with some sort of standardization. But usually everyone does it in a different way. XCM is really, like, regardless of how you use it, it's really just a language to standardize what people want to do in a blockchain. So for example, you have instructions for sending tokens, you have instructions for doing swaps, you have instructions for executing smart contracts. So you have, it's that sort of tries to standardize what people want to do on a blockchain, and then allows the actors involved to send those messages between them. The adoption of use of XCM on other ecosystems, it's not there. They prefer to create their own thing. Also, we don't do a lot of, like, most people see XCM and they assume it's Polkadot, and they assume that they cannot use it because it's Polkadot. The same way they assume they cannot use some, I don't know, the Cosmos thing, which I forgot the name, because it's Cosmos or whatever. Like, it's very hard to convince someone. It's really also hard to convince someone that they can use Frame outside of Polkadot, right? But you can use Substrate outside of Polkadot. You can use Frame outside of Polkadot. You can use XCM outside of Polkadot. You can use all our ideas outside of Polkadot. So, like, if you think about it, Polkadot is it's the playground where we use all our things, but all our things are really meant to push the Web3 vision forward, and anyone can use them. And honestly, I think the Polkadot SDK, or like the Frame and Substrate, is the coolest framework, obviously totally biased, but the coolest framework to build blockchains with. Like, I think it's general, it's very general. In particular, like Rust, maybe you like something else, so you might use something like the Cosmos SDK. And then XCM is a good way of, I think it's a good attempt at like standardizing what you can do with blockchains. And yeah, but it's practical use outside of Polkadot has not been that low, a lot. And then there was a second question, which I need to remember.
I can repeat it.
Yeah. Okay,
Yeah.
please, like just a short version. I will remember.
Like how,
yeah.
like whether in Polkadot,
Reverts,
the
right?
verification, like the
Yeah,
revert.
so reverts, we'll talk about it later, but it's not up to the developer of the message, if that's your question. So if the application layer was building a message or making a smart contract, like the application layer, it's not up to you. It's up to the infrastructure layer. So it's either up to the transport protocol or whoever is building the chain. So we learned about building chains. That is infrastructure. That is the platform. That is the underlying thing that systems run on. When you're using XCM, you're just writing the programs and you don't care about, you don't code in the verification. I mean, you can, but in general, the infrastructure layer will provide some sort of verification for you. Like, for example, when you use Snowbridge and you send a transfer from Polkadot to Ethereum, you don't need to specify, hey, revert if something bad happens. The system will take care of it. Now, they do not revert it in the traditional sense because it costs a lot. It costs a lot already to send things from A to B. So if it fails, like on the destination, it will cost a lot as well to take it from B to A. So in general, you leave it on B stuck in some way, in some place where the sender can send the following message to claim it, like to claim some trapped funds and do what they wanted to do with them once they fix their bug or something. Okay. Does anyone else have some questions? Yeah, a question over there, and then one at the front.
Hi, Carlos. Yeah, I have 3 questions.
Wow.
No, they're simple. The first one is roughly, what would you say is like the percentage of the crypto world that speaks XCM? So, for example, if I speak English,
Polkadot, yeah.
only Polkadot.
Yeah.
So
Ethereum as well, but only in the communication between Polkadot and Ethereum. Yeah. So not a lot of work has been done in trying to convince other ecosystems to use XCM, sadly. But yeah, the idea of an intention-based system, we have had it since XCM. I don't know when it was envisioned. And then now ecosystems are coming up with their own, they're coming up with the idea that they need an intent-based system, but they're creating their own thing. Yeah.
Yeah, that would be my second question. Which are the incentives for other systems to implement XCM? So
I mean, yeah, what are the incentives of speaking English? Like, lots of people speak it. So what are the incentives of speaking XCM? Not that many if not a lot of people speak it. And if it's only Polkadot, if you like doing things with Polkadot, then yes. But if not, you will probably use some other like Ethereum thing and so on. So that's why we're trying to push for, yeah, getting more users to use our things and making it easier to access things like Ethereum with bridges and so on. And then it will hopefully become more useful to implement or to, speak XCM. Okay, and the third one was answered already? Or?
Was answered already.
Okay. Yeah, here.
Thanks. Could you give a couple of examples of the most common intent messages that are sent?
Yes, I just started. I will give a lot of examples, and you will even code the things yourself. So yeah, but so examples I just said, like it could be a cross-chain transfer, which is the easiest. Just send in some dot from Polkadot to Ethereum, for example. Then you could do cross-chain swaps. So for example, you are on a parachain on Polkadot, and you send the message to Hydration. You do a swap, and it returns you the result of the swap. And then you can even do just like I send a message from one parachain to Moonbeam, and I execute a smart contract, and I return whether or not it was successful or not. So I think like transfers, swaps, and executions, like arbitrary executions, are the most relevant ones right now. In the future, we might have more, or we might see more. Good. So all of the images are dead. So there was an example flow. This is something that probably changed because of the structure of the repo. So I don't know if Nikos can fix it. The images are pointing probably to the wrong direction. It's my fault, apparently. There,
It is a XCM message, XCM from source chain to a wrong destination chain.
yes. So there were a lot of things being pushed and merged and stuff moving around. So yeah. But yeah, next steps we will take a look at this. I will show you the actual image. It doesn't matter if it's in the slides or not. It is in the repo. And then I will show you the next steps is to learn about the primitives that make up XCM. Yeah, over there.
I also had the trouble on the website. Locally, it worked. Like when I build it locally.
Yeah.
So if
It
you
worked
have-
on my machine.
Yeah. So you might also just try switching to your local so you can
What?
show it.
Okay, let me just switch to local, which I know is in evil or something, but it's the way to go. PBA content. Let me just pull and then yarn start, I think. Nice. So here you can see, of course, all of the XCM stuff. You see this transfer protocol in XCM. So the example flow is like you got two parachains. Like, yeah, we talk mostly about parachains because the other thing is will be just like from Polkadot to Ethereum. So you have a user, Alice, that submits an extrinsic to Asset Hub, right? All good to a parachain. And then that extrinsic results in an XCM program being sent to another parachain, telling to transfer like 5 DOT and 10 USDT, for example. This is just a cross-chain swap, just cross-chain transfer. We will use this as an example across all the lectures. And then this parachain would deposit the appropriate funds to Bob, right? So this will be a cross-chain transfer from Alice to Bob. And we will dissect this flow on all of the following lectures. That's our example for now. Okay, let's keep on going then. Polkadot Blockchain Academy, XCM primitives. So we have a lot to cover, but yeah, a question? Okay, but we have a lot to cover, and you already know the topic, like what XCM is. Now let's first see the primitives. And the primitives will be probably all we get to see before the break, the break at 10. And then we will look more at how it's actually executed and so on. The primitive is still a little bit of theory. Yeah.
Okay, please feel free to post that question if it's going to be answered later. About specifically the bridge to Ethereum.
Yeah.
Is that a dedicated parachain that's whole functionality is to have an XCM messaging and then talk to Ethereum some way, or?
Well, so from I don't know, from the point of view of the application, it doesn't matter. For curiosity reasons, or maybe if you want to work on it or something. So just to know what it is, it's not a parachain, it's just some code, right? Some logic that right now sits on a parachain called the Bridge Hub, but it will be moved to Asset Hub, so it will be just part of the whole Polkadot Hub package that some of us have talked about before. So the code for Snowbridge, all of the functionality of the bridge, will be just part of the whole Polkadot Hub package. So you will have Ethereum-compatible smart contracts, you will have access to governance, staking, assets, and you will have access to a bridge.
All right. Yeah, and of course, this would be a preferred policy. Try to convince the community to include this in the hub parachain.
So if a parachain wants to send funds to Ethereum, it can just send a message that goes.
Can use that piece of code, copy paste that piece of code on my.
No, not copy paste. Use the existing infrastructure. So that's that's why I'm mentioning this, because it's a very important distinction. Every chain does not need to implement the same thing. That's the whole point. So if a chain, for example, let's say we have stuff on the Asset Hub, right? We have the bridge and Asset Hub. You don't need Like if you're a parachain, maybe if you're hydration, you don't need to copy and paste the code to do a bridge to Ethereum. You just write an XCM
Message.
program
Ah.
that goes to Asset Hub. And remember, they can do a lot of things. So you can go to Asset Hub and then go to Ethereum. You can even like pick up stuff along the way. So you can pick up tokens on hydration, go to Asset Hub, pick up more tokens, and then go to Ethereum.
Okay, so yeah, I thought I copy paste the XCM message. I'm not talking about the relay or anything. It's there. I'm talking about.
Okay,
Yeah.
Yeah, but I mean, copy pasting. It's just like, I don't know, 30 lines of code, 50.
I'm not. That's not what I'm.
Okay,
worried
no,
about.
no,
What I'm
okay.
worried
Copy
about
pasting
is-
sound more overkill.
No, not really. It's not that much. I know.
Okay,
But
okay.
again, what I'm talking about is there is a parachain in the Polkadot ecosystem, which is called Bridge Hub,
Yep.
which I'll be using now. I have a new parachain
All right.
that sorry, a new outer chain.
Like a solo chain.
Yeah, another totally different chain.
Okay.
So it's not in the Polkadot system, and I want people to be talking to it. It should be first in the Bridge Hub, right?
I mean, so the Bridge Hub thing, maybe I shouldn't have mentioned it, but it's like, did I? No, okay. It's just infrastructure that users don't need to know about. Now, yeah, if you're talking, if you just have a bridge, if you just have a chain, you just implement your own chain and you want it to connect to Polkadot, then yes, you would implement your own bridge by, in this case, either copy and pasting or like changing some parameters. You definitely need to.
Let me rephrase my question.
Okay.
So there is no bridge now. Let's say there is no bridge now between Polkadot and Ethereum.
Okay.
And I thought I'd want to make one.
You can,
Okay.
yeah, make one, yeah.
Okay, so I own Ethereum, and I'll do whatever is needed on the Ethereum side.
Okay.
Now, on the Polkadot side, what I'm going to do, include some piece of code and
In your chain, if you want to, yeah.
I don't own Polkadot. Okay, I
No,
only own
okay.
Ethereum.
So that's why, for example, that's something that Hyperbridge does. So you don't own Polkadot and you don't own Ethereum, right? The whole point is that no one owns anything. Sorry. The whole point is that everyone owns everything, but collectively, right? Like there's no one owner. So yeah, in Ethereum, you can do smart contracts. Great. And that's how people do bridges. If you wanted to do a native bridge, you would need to be like an Ethereum core developer. People would need to get you in, and you would need to do like a meeting with all of them and then get your code into the actual Ethereum protocol. In Polkadot, it works the same way. Right now, we don't have, for example, smart contracts on Asset Hub, but we do have smart contracts on Moonbeam, for example, and we do have a wormhole smart contract, which was developed by someone on Asset Hub, on Moonbeam, to connect to Ethereum. Now, we also have the ability to create rollups natively and easily that Ethereum doesn't have. So if you want to create a bridge, you can do like Hyperbridge, which is its own parachain, and you can create your parachain, and you can create a bridge, and you are the owner of all of the logic of that parachain.
Okay.
Snowbridge was like, it's a team that was voted in by a referendum that they should be able to add their code to the system chain, which is Asset Hub, which is not like built by anyone, it's built by the core developers, and that's why Snowbridge is in there. But for example, if you want to use Hyperbridge, you just build an XCM that sends stuff to Hyperbridge and then accesses Hyperbridge functionality. So it really is very much permissionless. If you want to build something, you have a lot of avenues to build it.
Okay, just XCM messages. Ethereum is something new, something totally new. I don't have to change anything in the Bridge Hub logic.
No.
All it needs is that custom XCM message that I'll be sending to it, and then it then can talk to Ethereum or whatever, anything else.
Yes. So this question
My
is
own local server.
Yeah, so this question is it's not so much about XCM, and if I find that that's the case always, like it's not about XCM, it's about the other things. So in this case, what you're asking is, how do I deploy on Polkadot? How do I code apps on Polkadot? How do I make a bridge? then the answer is you either do a parachain or you do a smart contract. Those are the two sort of entry points for developers that we have. And that's it. And then XCM lets you access functionality from other chains. Sure, but that's just it. Like XCM lets you use functionality from other chains. But you can, if you want to make a bridge, the same way if you want to do anything, you can do a parachain or you can do a smart contract. Okay, good. So let's keep on moving because I think this is not that related to XCM. If you want to make a bridge, you can make a parachain. If you want to make a bridge, you can make a contract. That's it. Now let's keep on moving with XCM because we have a lot to cover until the 10-minute mark, the 10-hour mark. Good. So I will move on, and then I will answer questions after a while because I want to get some content into your guys' brains. So what we will learn before the coffee break, hopefully, is about locations, assets, and instructions. So all of XCM uses these things. Like how do you reference where you want a message to go? We created this notion of locations to standardize where you want the message to go. Like you cannot just have where you want to go be a string saying all the chains that exist right now because new chains might come in. So we have the concept of locations. We have the concept of assets, like how do you reference assets in your programs? And then the instructions themselves like what things can you do? So these three things, all of the fundamental building blocks. Locations. So it's a way of referencing any entity in the network, for example, the recipient of the message. So if you are just a random Alice, right, and you have a message and you want to send it to someone, how can you send it to Bob? How can you send it to Asset Hub, to a particular pallet? Maybe it's a like pallet-owned account or something, or to a particular smart contract. We need a way, okay. We need a way to be able to talk about these things. Like how do you say, okay, I want to send a message to Ethereum. I want to send a message to a particular smart contract in Ethereum. How do I send a message to Polkadot, to Kusama, to this account, to this parachain? Locations is a sort of URL of blockchains, right? Like how do I access a particular blockchain? How do I get there, right? What's the path to get there? So locations are basically paths. It even says location with the like URL analogy, right? It's like a unique location. And they could be relative or absolute the same way as URLs can be. And regarding this relative and absolute, let's talk about interior location. So there is a location hierarchy. Some locations are sub-paths of other locations. So for example, given two consensus systems, A and B, A is interior to B if a state change in A implies a state change in B. And you read this, and it's really hard to know what it means from just like reading it one time. But the idea is you have for example, you have a chain, and that's a location, and you have an account on that chain. That account is an interior location to that chain. Why? Because if that account changes, like if the balance of that account changes, then the state root of the chain changes as well. That's the idea. Like anything that your chain has, if that changes, then the whole state root changes. So there's a hierarchy of locations, which we can see here. So we have this is for Polkadot. So let's say we have the relay chain. Then interior to the relay chain, we have parachains A and B. Why? Because if a parachain A changes any of its state, the relay also needs to change the state because the relay keeps track of all the parachains' state. Of course, this happens in a multi-chain environment like Polkadot and Ethereum. Sure, you have L2s, but they are not so built into the protocol. They basically act like any other actor. But this is why we have like interior locations. And then every system has like accounts, which are interior to the chain they interact on or they exist on. And then you can have pallets as well, and smart contracts, for example. All of them make a hierarchy. So how do we define a location in Rust code? We have a struct called location, which has a parents field and the junctions field. So the parents is how many times you go up. In the URL analogy would be dot dot slash, like how many times you go up, the hierarchy that I just showed you. And the junction is how many times you go down, but like also which thing you use to go down. Because as you saw, there's only one way to go up. Oh, my bad. As you saw, there's only one way to go up, which is to go to your parent location. But there are multiple ways to go down. You need to choose which path to pick. So that's why we use a U8 for going up for the parents. And we use junctions to go down, because your junction might be, hey, I'm on the relay chain, right? I want to go to a parachain, I use this junction. I want to go to an account, I use this junction. A palette, and just a number in case you have something that cannot be represented by any other junction, you can use a number, or you can use a network ID, sort of like I go to Ethereum, Kusama, Bitcoin, and so on. Yeah, the network ID can be by genesis, which means I identify the network by its genesis hash. That's like the most generic one. Like you can just put the genesis hash and you identify the network. It can be by fork, Polkadot, Kusama, Ethereum, Bitcoin, Cash. Yeah, those are just some enums that we've defined, right? And remember, this doesn't. We're still not talking about like functionality. We're not talking about how to interpret these things via code, but this is the address of things. In the blockchain world, this represents the address of everything. Yeah, and we have like a very useful text notation, which is like if you have a location with parents 1 and then interior parachain 50, then you might see this, right? It might be this URL. So hopefully, if you're used to this in like folder structures, you will see the analogy that here you're just going up a level and then you go down to a parachain. And this is a relative location because you have to go up, right? And we all know this from file systems. Like this is a relative location. It depends on where you are. The interpretation of this dot dot slash parachain 50 depends on where you are. Whereas if you just had like slash and the rest, it would be an absolute location and it would always start from one point. Let's talk about that point. So we want a root of our blockchain world file system. Like if the blockchain world were a file system where you can do dot dot slash parachain 50 to go up and then down to a parachain, we would want to have a root, right? A root that lets us have absolute locations of where do we go. That root, we call it the universal location. The universal location is sort of the root where you start, and then you go wherever you want to go. Now, it is a theoretical location. It's not a chain. Like we cannot say Polkadot is the root. We cannot say Ethereum is the root. We cannot say Bitcoin is the root. So we just say the root is the universal location, which is theoretical. It's the parent of all locations which generate their own consensus, and it itself has no parents. So if you have no parents and your children, your immediate children are things that generate their own consensus, so things that have validators and generate their own consensus, then you are the universal location, and you can imagine it as just, it's quite small, but you can imagine it as just one universal location that doesn't exist. It's a theoretical thing. And then all the children are blockchains that generate their own consensus. So that have a set of validators and are generating their own agreements on things. Because for example, if you are a parachain on Polkadot, yes, you have your own sort of consensus, but you will impact Polkadot's consensus. But if you are Polkadot and Kusama, you're pretty much independent. If you are also Ethereum or Bitcoin, you're also independent. So the universal location is just a way to allow you to write things like, if I'm on Polkadot and I want to go to Ethereum, I can do things like dot dot slash Ethereum, right? And we will talk more about this later if that didn't click, but I'm just giving you a heads up. It's as simple as that. If you got it, if you didn't get it, don't worry, we'll talk more about it. So now that we have this universal location, we can actually have a root, and we can specify things via absolute location. So an absolute location, it has this type in Rust, which is called interior location, which should be called absolute, but yeah, which is only it's only some junctions. There are no parents, because if you are the root, you cannot go up. And the first junction has to be this global consensus junction that we have, which will identify a network itself. So it's not a global, it's not an absolute location to say / parachain, because parachains don't exist in the ether. You need to do / global consensus and then a network ID, and the network ID could be Polkadot or Ethereum or Bitcoin, or it could be a Genesis hash, and you're identifying a new blockchain that is not one of the ones that we have, but you can identify anything you want, right? It's a very general system. If something doesn't exist, there's always an escape hatch to define just by Genesis hash, for example. Now that we talked about this, what are these useful for? They're used for addressing where you want things to go, origins, where something came from. So now we have a language to speak. Like if a chain receives a message, they can now see like where it came from, and they use this format. It came from parents one interior parachain, means that it came from a sibling parachain, like from another parachain on the same Polkadot network. Or maybe it came from Ethereum, or maybe it came from Bitcoin. It doesn't matter how the message got there. Because you just assume if there's an origin that tells you something came from Bitcoin, it means there must be some sort of transport protocol that sent it from Bitcoin in some way, right? Some bridge. But the language itself, the notion of locations, doesn't care how that is possible, right? It only cares that given that location, what you do with it. So it's useful for addressing, it's useful for origins. I think you can see my mouse, yeah. So addressing, origins, assets, fees, and bridging. So when I say bridging, I just mean you can specify you want to send it to Ethereum. Assets is like, I want to send this particular ERC20, which lives on Ethereum on smart contract ID, right? We'll talk about that later. And then fees also, they're used for everything pretty much. So it's the most useful concept, I guess. Good. So cross-chain origins. Now we talked about like how to know where something came from. When a receiver gets an XCM, a location, so the thing that we saw before, which is this. Sorry, this. This is in Rust, right? It could be implemented in TypeScript, in whatever you want. So this is what the chain sees as where it got things from. It got things from some location, which has a number of parents, and then a number of junctions. The location is relative to the receiver, right? If I receive a message, the location will be relative to me, and the transport protocol would make sure that the location is relative to me. And it can be converted into a palette origin in a frame runtime. We've talked about this briefly when we talked about origins, which is you can create in frame custom origins. I think you're all very used to that, or at least know that you can do it. And you can make a system where if you receive a message from another chain, you create the frame origin, like a custom frame origin that means, okay, this came from a parachain, right? An XCM origin is different from a frame origin, but you can convert between the two. For example, let's say you have an account ID location or junction. You can just have something that converts an account ID 32 into a frame signed origin. right? So this system is not coupled with frame, as all of the things we do, they're not tightly coupled together, but there's an easy way to go from one to the other. Hopefully you can see that. If not, it will click over time. It is used for determining privileges during XCM execution. So you are given an origin, and that origin will let you know what you can do. So if you're just an account, maybe you cannot drain all the funds from the chain. But if you are another chain, maybe you can drain all of the funds in that chain's account. If you're the root, then maybe you can do everything because you're a root. It depends on your origin. And your origin can be, which I didn't show, but your origin can be here, right? It could be // it could be here. And if it's here and you're a chain, it means it's the root of the chain. And if you're the root of the chain, you can do whatever you want. Good. And now let's go through like a bunch of examples. So this sits well with you. Again, I want to mention that this is not, so like the fact that you can write a location doesn't mean there's a way to get there, doesn't mean anything really. It just means that you're writing an address. Like I can of course write an address of a street that doesn't exist. It doesn't mean anything. And if I like write a letter and I put an address that doesn't exist and I send it to the post office, then it will just never get there. That's the same idea with XCM. Like you can write any location you want, but if I send, I want to send a message to Bitcoin and there's no Bitcoin bridge, when you send it into the system, it will just give you an error saying, hey, I know you want to go to Bitcoin, I just don't know how to get there, and you will get an error. But locations is just this language of street names, right? That's very important. So let's see examples of this. We have Polkadot, we have Asset Hub, and collectives, for example. Collectives is another system chain. So Asset Hub is ID 1000, and collectives is ID 1001. This is just, each chain has a parachain ID. Each parachain has a parachain ID. So what if we are in Asset Hub, and this is indicated by this little marker, like we start from Asset Hub, and we get the following relative location. So let's say the relative location means I'm on Asset Hub, and I want to send the message to somewhere. And in the destination, I put this. Where would I go? Now I want someone to tell me. You have to have a mic, or? Yeah.
I believe like you need to go through the bridge hub or something like this, where I'm saying this is a parachain thing, like.
Okay. Any other guesses? There are, yes, some at the front and at the side. Whoever gets there first. It's a race. There you go.
So we will hit the collectives, right? We will go up one
Yep.
and to the collective.
There you go. So you will go up one, and then you go to parachain 1001. So you go to collectives. Now, this process of going up once and then going to collectives is not a physical process. Like when you send the message, it doesn't necessarily have to go one and to collectives. This is just a way to reference where you want to go. So when you're an Asset Hub and you want to talk about collectives, for example, look how cool the stuff that they're doing in collectives is, you will talk about this chain as the sibling chain with ID 1001. You would go up one, and then that's how you reference it. So there's no, we will see an example about the bridge to Ethereum, and we will see that the location doesn't need to correspond to the actual physical path that the message will take. Locations are just like street names. You don't care where they go from. You just care where they get there. So here's the full thing. I couldn't get arrows to work in Mermaid, but imagine there's an arrow there and there's an arrow here, right? They go in and up and down. And I don't know why I put it dashed. There must have been a reason. Maybe because it doesn't have to go to the relay before going to collectives. Okay, another idea. So what if we are on Polkadot? And so that's where we start. And we have the collectives chain, which we saw before. We have asset hub, which we saw before. And now we have an account ID, right? 0x1234, and it continues. We're on Polkadot, and we want to send a message. And in the destination field, we put parachain 1000, account ID 32, and yeah, 0x1234. So which one are we referencing here? Yeah, there's someone there, but it doesn't have a mic. So, but yeah, you pointed it, right? So you're going to the account ID. This one doesn't have much of a mystery. So you're going down. Hopefully, this is understandable. Now let's talk through the bridge, which might be kind of like a confusing one at times. So let's say we are on Asset Hub. Now this is a more complicated topology of the network, right? There are two networks, Polkadot and Kusama. You might have heard about Kusama before. If not, it's just also a substrate-based network. We use it as a canary network for Polkadot, but they're independent. Okay. So there's a universal location up at the top, which is the root, which doesn't exist. It's not a chain, but we use it to make sense of locations. Then we have Polkadot on one side, Kusama on one side. Both of them have Asset Hub and Bridge Hub. Again, Bridge Hub is just an infrastructure thing. It doesn't need to be there, actually. And maybe in the future, we would just implement everything on Asset Hub. Who knows? But it's just a chain. It's just a parachain. A system chain, but it's a chain. And then Asset Hub has like an account Alice, and then it has like an assets palette and USDT, for example. Like Asset Hub has a USDT register there. So you are on Asset Hub and you receive ... global consensus Kusama parachain 1000. Now this one I will ask someone to take a guess. Asset Hub 1000, then the Kusama, exactly. So I'll just repeat, because taking mics takes a while. So I'll just repeat what he said. So you are on Asset Hub on Polkadot, and by using this location, we all know that you're talking about Asset Hub on Kusama. Right? This is another reason why we cannot just have like an enum of all possible strings and the string being Asset Hub, because it's Asset Hub on Kusama. Yep?
I have a question.
Yep, let me
One of
just
your
check.
prior slides said that the location is relative to the receiver, but it
Yes.
looks here like the location is relative to the origin.
Yes, so when I said the location is relative to the receiver, I said it's when it's an origin. So when you are the receiver, you will see who it came from, like the recipient, and that location will be relative to you. But when you are the sender, you will send the message and you will write a location that is relative to you as well. In the middle, like the location that the sender specifies and the location that the receiver sees, in the middle, the system will just switch it so that everyone has an easier time dealing with these things. There will be a switch from perspective, right? But the only thing you need to know is if you are the receiver, you will see the location relative to you. If you're the sender, you will specify the location relative to you. So just to complete this example, because I moved from the slides, you go up to Polkadot, up to the universal location, down to Kusama, down to Asset Hub. That's how you use this to reference Kusama Asset Hub. Yeah.
This is very similar to how we find locations in the file system.
Yeah, exactly.
And the message passing is also very similar to that. It doesn't trace back to the root. I mean, the file doesn't move from here to root and then go back.
True.
Just
Yeah,
moves.
yeah. So we try to use that analogy as much as possible. That's why we have the location there in like file system format. It's really just that. It's like a URL, right? Yep.
Can you explain why it's brackets Kusama and not / Kusama?
Brackets
Global
Kusama.
consensus.
Oh yeah, because we have a lot of junctions, and the junctions are like, for example, we have a junction called parachain, which you need to specify the ID, and we have a junction called global consensus that you need to specify the network ID. So we do not have a junction called Kusama. We have a junction called, okay, this is a network, and then you specify the network ID, you put Kusama, or you put my genesis, and you can reference anything you want. As long as you know the genesis, if you see by Genesis and some Genesis hash, you can like check which network you're referring to. Let me pass. Okay, so this is how you reference, and yeah, as Naren said, like you don't, even when you're moving a file, it doesn't move to the root and then it moves to the end. It has a different movement. And here it's the same thing. Excuse mermaid JS that will put them in a weird state, but you have asset hub, Polkadot, and the universal location. The actual routing will probably be asset hub, Gusto bridge hub. There's a bridge going on between bridge hubs, and then it goes to Kusama to asset hub. Like that would be the actual movement of the message if you were to send it, but how you reference things is still the same. Also another very important thing. Okay, and then we're done with location examples. So hopefully you all know what's going on there. There's a question, yeah?
Yeah, so we know that Polkadot and Kusama are two differentiate. How would, like, it looks like you can probably do test nets as well, like West.
Yeah,
So
exactly.
how do you prevent messages from, like, because those are not real network, like, so how do you prevent that messaging from going?
Well,
Or do you want to?
Yeah, so that's another good example of confusion with like the fact that you can write a location doesn't mean there is a way to go there, right? The fact that I can write, well, as Naren said, yeah, keeping up with the file system analogy, the fact that I can write / directory that doesn't exist / something else / doesn't mean that it's there, or doesn't mean that there's a way to get there. In file systems, yeah, it means that it's not there. There's always a way to go from A to B. But so you would just not have a bridge between testnets and mainnets. And then if you're in a testnet and you want to send a message, and in the destination you put like Polkadot, the testnet will, because it's configurable, the testnet will see the location and be like, okay, I don't know how to get here, and it will just return an error. Okay, that's also a very crucial aspect of all of this. Okay, yeah, question over there.
Yeah, it's still like in the location part. I'm just wondering if will be any difference between the locations URL. Let's say it like this. If I'm sending between parachains, like in without accessing, like going to other like network or not, I understand the fact that like if I am in the AST hub here and I go to like the other like parachain connecting to it, I know the route. I understand the part of the route, but I'm asking about like the full location. It will be the full location starting from the universal location, or it will be only the small part I want to access.
Yeah. So if you wanted to go, so yeah, you can reference. So because relative locations came first, and they do have some advantages. I think there was a slide on like relative versus absolute locations.
Yeah, it was one of my question, like when to use each one of them, you know?
Yeah, it depends on what the system expects. So if the system expects, also the system could use both, right? If the system receives something that has no parents and starts with the global consensus junction, it will switch mode to, okay, this is an absolute location, just like in the file system where you can use both. And if it starts with a dot, you're like, okay, this is relative. And if it starts with a /, you're like, okay, this is absolute. The system could just deal with both of them. We do have systems that just expect a relative location, which might be annoying at times if you want to use an absolute one. That might be something that we change in the future, but yeah, I mean, because it's already there, it takes a while, or we might never do it. But you can use relative or absolute, or you can definitely design a system that uses absolute everywhere instead of relative, or that can use both.
I'm confused when you mentioned like systems or design systems.
The blockchain, sorry.
I mean like, yeah, like
a chain.
For me, like, does it mean that Kusama, for example, has their own way of XCM and Polkadot has their own way, and I need to, if I'm accessing Kusama, I need to care about how they are like setting their location standards?
No, so you don't need to care, but they do have their own way, like they do interpret the things that we're talking about, they do interpret them in their own way, because we want to allow for multiple different things, and we want to allow for things like runtime upgrades. So I might have not mentioned this before. I mean, I mentioned it, but I don't think there was a slide for it. But if you are sending an XCM, not just locations, but also instructions and so on, and you're sending an XCM from Polkadot to Kusama, and Kusama does a runtime upgrade that changes things, like it literally moves 2 pallets, right? So now the indices are different or whatever. Then, well, first of all, if you move 2 pallets, the instruction is still the same. But yeah, you need to interpret it differently. And we allow for each chain to interpret it differently. The language is a universal thing that tries to standardize what you can do and how to reference other places. But each system, so each chain, can decide how to interpret them to fulfill the requirements or the expectations of the sender. But yeah, if you want to send a message from A to B, you do not need to care about what B expects. You only need to care about what A expects, because you are sending something. So maybe in Polkadot, you can put in the destination field when you are sending something, you have to put a relative location right now. If you put an absolute, I believe it will not be able to route it. But that's just because we designed it that way. It should, yeah, if you put an absolute or a relative, just figure out which one it is and do another logic. But
And the transport layer would understand that like this is okay, like, or just like it will see it as a byte and that's it. There is no kind of like
the transport layer wouldn't see the destination in a location. It would just be called by the application layer. So it would be kind of like, yeah, I don't know, like the location is kind of like an IP address, right? And then the transport layer kind of just do the Ethernet thing, like network. That's how you can think about it. Okay. Yeah, another question.
2 questions. One question, is there a utility that allows you to convert from relative to absolute
Yes.
locations? Okay.
Yep.
All right. And the second one is, going back to our earlier conversation, you mentioned that the system switches the relative location. Is that, does that happen when it goes from extrinsic to event? Is the extrinsic relative to the origin and the event relative to the receiver?
Yeah. So extrinsics and events are concepts of frame, much rather say like the sender and the receiver. But yeah, so the sender would probably, there would be some extrinsic that will initiate the sending. That would be on the sender side. And on the receiver side, yeah, there might be like an event showing what happened. Now you might or might not put the location in the event itself. But yeah, so when we send a message from Polkadot to Kusama, for example, you specify like Kusama, like / Kusama, and then the system would re-anchor your location. So we would just change it from your perspective to Kusama's perspective, and we'll send a message to Kusama, and Kusama will see it from their perspective. But that's something that you don't need to care about on the application layer. But yeah, the receiver will receive it from their perspective. If it was a universal location, for example, if it was an absolute location, we wouldn't be surprised that like one guy specifies, I'm going to Kusama, and then Kusama says, oh, I got it from Polkadot. The fact that it's relative just means we need to change it in the middle, like re-anchor it, switch it. But if it was absolute, then it would be the same thing, just pointing to the other. We need to change it anyway, right? There's no way we can pass it.
Well, the reason why I'm asking is like in these examples, it's very simple because you're putting a lollipop, which tells you where to start.
Yeah.
In the real world, there's no lollipop, right? You have to figure all this stuff out on your own.
There's no lollipop. Yeah, but the receiver tells you where they got it from. And they are like, for example, there are websites like, maybe we can make a little, I could show you this later, but there are websites like XCM, for example, that shows you like all of the messages that are sent. And they do track on-chain data, so they track like events. And they let you do things like, oh, this message came from Polkadot Bridge Hub to Mythos. This message went from Bifrost to Moonbeam, and so on. And if you go in there, you can see like like, yes, there are some, I don't know, quirks of the system, but it's understandable, it's knowable, and you can create off-chain applications that show you all of this. Like, I'm not saying you need to know locations and all of this stuff to use Polkadot. Of course, I'm not saying that. But if you want to make like an off-chain UI that shows the regular user how this works, you do need to know the underlying aspects of the system, right? Just like you would expect. Like, I don't expect a user of Polkadot to know what a location is. I would expect them to use a shiny UI that does everything for them, but that UI has to be developed knowing the actual system intricacies. So for example, this one knows the events that are emitted, knows what locations are, and will show you this. We can tell you more around that later, because it's a very nice website. Good. Now, let's talk about sovereign accounts. This is another thing that might be weird at first, but I think it really makes sense once you, it clicks at some point and you realize it makes a lot of sense, which is, even without the text that is on the screen, let's maybe go a little bit to the previous slide. So no, do not think about the slide. How, let's say, that hydration, the chain hydration wants to have some funds on Asset Hub. Like the whole chain, so maybe they did a referendum, right? They all agree that they all want to have some tokens on Asset Hub itself. How do we, on Asset Hub, how do we say, okay, hydration has this amount of funds? Because the hydration doesn't have an account that holds the tokens. It has, we can reference it via location, true, but locations are just a string, right, or some bytes. They're just the address to hydration. So what we do is we have this concept. It's still something we want to do, right? We want chains to be able to hold tokens on other chains. It's a very useful thing for many different reasons. We have this concept of sovereign accounts. Sovereign accounts are locations external to the local system that can be represented by a local account. This is a sort of frame thing, right? Because in XCM, we don't care about accounts. In Frame, we do care about accounts. These sovereign accounts are a way to turn a location into an account. So they're just some computation, like just some formula that gets you from a location, like / parachain 50, into an account. Now, whenever you ask, like, hey, how many dot does hydration have on Asset Hub, you can just stand on Asset Hub, use the location to hydration, and convert it into an account, and look at the account and see how much they have. We call this account that it is owned by another chain, but is on another chain, is on our chain. We call it a sovereign account. So for example, we have this account on Asset Hub. It would be the sovereign account of hydration on Asset Hub, right? Like the sovereign account of someone on somewhere. And they are basically just a mapping from a location to an account ID. Yeah, we have some questions up here at the front. Sovereign accounts is another thing that we use a lot, and it's very important.
Like when we see it from the perspective of, let's say, two parachains, and we have one sovereign account, is it like some of the hard fork or soft fork of your account, or
no?
How is it represented?
Yeah, so I guess when you say fork, you mean like a derivation.
It
It has nothing to do with like cryptographic derivation. It's just we want to assign, like we want another chain to be able to have an account on our local chain. The way we do it is we do use some function on the location that references that chain that will return an account ID. And you can do this however you want. In Polkadot, we like grab each junction and we hash them and we concatenate them and we end up with an account, right? Like as you saw with the treasury example, there's a way to create like a pallet-owned account. We have a function that grabs a location and it will do some things and return you an account. So it will hash and concatenate and hash and you get an account. So it's just a way to go from location to account, and that will give us an account that is owned by another chain.
Okay, thank you.
Okay, there's one behind you. No, so immediately behind you, yeah, and then you, yeah.
And are these account IDs chain specific or I don't know, a location with an absolute location has the same account ID in different? chains?
No, they are location specific
Okay.
because you are a sovereign parachain or chain, and you can choose how to convert a location into an account. But the good thing is XCM doesn't care. Like, let's say you want to send, so we had an example before of Alice sending a message to Bob.
Yeah.
So let's say instead of Alice, it's like some sovereign account of some chain, and then Bob, it's some other sovereign account, for example. It doesn't matter that the account would be different on different chains, because in the message you don't reference accounts. In the message you reference locations, and that's the magic. Like, they can interpret it how they want, and everything locally can work. And you work on this like abstraction layer where you only talk about locations.
Okay. Thanks.
Nice. And there's one in the back.
Yeah, like you just mentioned that when we talk about XCM, it's not related to frame, and now we are talking about frame. Is this how frame
Yeah.
converted? So if I'm not using frame, I have to do it in my own, or like how?
Yeah. So this is XCM is not like. I mean, it's clearly about blockchain, right? It tries to standardize what you can do on blockchain systems. But it's not tied to frame, and this is just one way to. Okay, I have these allocations. This is great, but now how can I turn a location into an actual frame account? You could have a system that just uses locations as accounts, kind of, because locations have an account ID 32 junction. You could have a system which is not frame, or maybe it is frame. Maybe you're using frame for your chain, but you design a system where your account IDs are not 32-byte hashes, but they're actually locations. And then, yeah, you just need some way to go from a location to an account. And it depends on what you're using, how you do that conversion. But at the end of the day, we need accounts because we need to hold tokens. And it's just a good, like, taking this concept of cross-chain into the local chain, making sure that everything works, and it's just an account at the end of the day. So for the account, like, let's see there's some application of chain that is looking at all of the accounts. They wouldn't know that anything cross-chain is happening. It's just a normal account. Okay, so yeah, I would have some examples of this. It's just like, and not only chains can have sovereign accounts, an account can have a sovereign account. Like, an account on one chain can have a sovereign account on another chain. So for example, here we have Polkadot, Asset Hub Collectives. In Asset Hub, we have an account called Alice, and we have an Alice's sovereign account. This Alice's sovereign account is just like some hash of the location, relative location from collectives to Alice. And so it's a different account. Like, this account might be, I don't know, 1, 2, 3, 4. This account might be A, B, C, D. It's a different thing.
Can I ask here, because like I'm confused to the top. The sovereign account here is like from the point of view of the XCM.
Yeah,
correct?
so here is relative to collectives.
It's like exactly like I want to send a message from the south chain. So this is the account I'm sending like there, and it doesn't have to be there.
I don't understand the question. Sorry. So maybe like how you get this sovereign account is not that relevant as like what it is, right? So you have a sovereign account, and the important thing is that Alice, which has an account with a private key and can sign things on this chain, also has a sovereign account which she owns, and whenever she does like an on-chain cross-chain transfer, she can move stuff to this account. Now, how this account is calculated, it depends on the chain, because it doesn't matter to XCM how you get this account. And we can later look at the actual function that gets you from a location to an account, because it's just a function that takes in a location and it returns an account ID. So we can laterally go into the code and look at it, and it probably, that doubt in particular, it will probably solve it. Okay, because with diagrams, it's kind of hard, right? With diagrams, I just want to show the different interactions of things. So we can also have, yeah, chains can have sovereign accounts. So this example just shows that Alice can have a sovereign account and collectives can have a sovereign account, Asset Hub can have a sovereign account. And this is how a chain or an account would, for example, this is how one account, Alice, could hold funds on multiple different chains. Good. Okay, so now we've talked about locations, which, if you remember, we have locations, assets, and instructions. So now we take a step back again. We have successfully talked about locations. They are a way to reference other things in the blockchain world. You might want to put like where I want this message to go. It might be an origin, like where this message came from. Yeah, those are locations. Now let's talk about assets. So I am going to write a program. I'm going to write an XCM program, and it will reference some locations, and it will also want to reference some assets. Like when I'm writing an XCM program, how do I reference DOT, right? How do I reference ETH? How do I reference other things? So here I'm just going to show you the Rust structures that we have. They are an asset. And here we want to be as generic as possible. So the asset will have an ID, and it will have a fungibility. The fungibility could be a fungible asset with a number, or it could be a non-fungible asset with an instance. Like maybe it's a non-fungible asset, and we will see a unique instance with an index 42 or with an index whatever. You can have an asset also represent an NFT. Anything that you might think of as an asset, you can, yeah. That's the fungibility. And then for the asset ID itself, we reuse the location. Why? Because it's very useful to, for example, let's say you want to reference an ERC20 token. And I think, because I know all of you, or a bunch of you are familiar with smart contracts, you might want to reference an ERC20 token that is defined in a particular address on Ethereum. So you would just, the ID of that asset would be the location of that asset. Like the location of Ethereum and of the smart contract. Now, how would I reference DOT? I would reference it, there's this convention, so this needs a convention of sorts. There's a convention that DOT is represented by the location to the relay chain. So if you are on a parachain and you want to reference DOT, you would use the parent, just the location that is parent1, interior, nothing. That will be DOT. If you want to reference USDT or USDC, they have a particular ID and it's assembled with a location. Good, so everything we talked about with locations applies for assets. So now you can specify, so locations are not only used for how do I send this to some place, who sent me this, it's also for what is this asset. And there are a bunch of other things, but this is the most important part. You can, as well, we define these filters, which is, okay, what if I want to make, okay, sure, I can reference one asset, but what if I want to do a cross-chain transfer with 3 assets, and I don't want to specify all of them all the time? So you just use a filter. And you can use a wild filter, and you have this filter called all, which is just like, you're referencing all of the assets that you have in possession. So when you do a cross-chain transfer, you can say like, okay, get me this ID, this ID, this ID, like these assets, and then deposit all of them to this account. It's just the notion of all, and we'll look at it. You look at it later in instructions. These are like used in the parameter of an instruction, like you get a filter. Okay, that's it. That's assets. It was just a very short thing because most of the knowledge comes from locations. So that's it. And now we're only left with instructions. So every XCM is a sequence of instructions. So the most important thing of XCM is just which instructions you have access to. But we needed to first cover locations because you will see those in the parameters of the instructions a lot. So I just wanted to cover them first. There are different kinds of instructions. So you have commands, which is do something. Trusted indications, which is like, hey, I did this. Please do something in response to this. There's an there are information messages, and then system notifications. So the system itself can send messages of, for example, a channel opened between, like a transport level channel opened between these two chains. They can actually reuse the application layer for sending system messages that are not meant for regular users. Most instructions are commands. I just have these kinds, but most instructions are commands of, hey, please do something. So now we see our first instruction, which is withdraw an asset. And it takes a list of assets. So maybe it should be called withdraw assets, but such is life. So when you use this command, all these instructions will be interpreted by some virtual machine, right? They will be executed, they will be interpreted. So this instruction, when it's interpreted, it will go into the account of the origin of the message, of the origin of the XCM, and it will withdraw those assets and like keep them in memory while the XCM is running, and for them to be used by subsequent instructions. This keeping them in memory we call the holding register. So because it's like a virtual machine, it has registers, and one of them is the origin, which lets you know where it came from, and another one is the holding, which lets you store stuff, store assets, so tokens. So when you do a withdraw asset instruction, it will take funds from the state, from your account, and will put them in the holding register, which is just a variable in memory. Like it will put them in memory. Then you have another command called deposit asset, which would grab whatever is on the holding register at that point in the execution of the program and put it into an account. Now, as you see, you have to specify an asset filter. So you can just say all, and it would be all of the assets that you have on your holding register. And the beneficiary is a location. So this location can be a parachain ID. And then the system would grab that parachain ID and would convert it into the sovereign account of that parachain ID so that it can actually like deposit things. But you always specify locations here. Of course, you can also use the account ID 32 junction in case you want to deposit into a regular, like user-owned account. Okay, so moving on, or maybe not moving on. Do you have is this? Yeah, let's move on. We have 15 minutes, and then we can do questions at the end. So there's another instruction called receive teleported asset, which takes some assets, which is, hey, I locked funds on the origin. Please mint them on the destination. Now, this is a trusted indication, which was the second option. This requires a lot of trust. Like when you execute this instruction, you will mint tokens because the other system tells you that they burnt them. Now, this requires a lot of trust, but this is what is used in teleports. So when we're talking about cross-chain transfers, we have two models, and they have two different trust assumptions. And you might be thinking, why would I ever do this if I'm literally just trusting another chain to do it? Well, maybe you're developing, maybe you're the Polkadot core development team, and you have a bunch of system chains, and like the same developers developed all of the chains. So you know the code is trusted, so you can just teleport between them. And it's just an easy way, like you know the code is the same, has the same owners, so you trust it. So you can just do teleports and that works fine. The other thing that you can do is you can trust the system. So yeah, you don't trust random code, but you can trust the system. So for example, you can trust Asset Hub, which is part of the system, to teleport something to you. The other model.
Yeah. Question. So when you say trust, that's potentially quite a loose word. Do you get any confirmation back? Like it's not a tightly coupled transaction as far as I'm understanding it, where part one is, they haven't burnt them yet, you're minting. So what confirmation do you get back from step one before you proceed to step two of minting?
You just trust that they did it in the teleporting case. So what it means, what I mean with trust, I know it's a loose word or vague word, but so if you think about it in a transaction sense, one step happens on one chain and the other step happens on another chain. So teleports, they require a high level of trust, and what it means is you're not checking that they actually did the burning. So you should never, ever, ever allow teleports from random chains. That's maybe a change from other on how other ecosystems use the word teleport. Like they just use it for mint and burn, and you need to make sure that they actually burned it and so on. Here we just separate the problem into two, and we say, okay, if you already trust the chain, and trusting the chain means they could already, if they were malicious, they could already screw you over. So for example, I trust Asset Hub because if you're a user that has tokens on Asset Hub, you trust Asset Hub. Sorry, if you're a user, you don't need XCM. But if you're a chain that has a sovereign account on Asset Hub and holds tokens on Asset Hub, you're already trusting Asset Hub because they could do, what I mean trusting Asset Hub is you're trusting the code of Asset Hub, because they could, if they wanted to, if they were malicious, they could take all of your tokens away. So you're already trusting them, for example, so you might as well allow them to do teleports, which is very, very easy because you don't do the check because you already trust them. Now, I know this sounds like basically useless outside of that scenario where you're like, another scenario. So there are only two scenarios where you might want to use this, or where you do use this, and we do use this. And then another one is the case for system chains. So system chains are all developed by the same team. So if the minting, if the burning was not done, it's a bug in the code. It's not that there's a malicious attacker. So, and yeah, there are ways of like handling the error that there was a bug and the assets get trapped or you get an error or so on. So we deal with it. But if you're building a system that you yourself are building 3 chains and they need to move stuff around, it's just so much easier and more efficient to just use teleports because you know you're the owner of the code. Now, this is not the model that is widely used for everything else. There's another model. We basically divide the problem of cross-chain transfers into 2. You have teleports, which are almost exclusively used with the system in some fashion, because they don't do the checks. And almost exclusively used within Polkadot, because you don't do the checks. But then the other model is useful for every other scenario, and it's the model that is used whenever 2 parachains don't trust each other. They're just sovereign chains dealing with something. Or whenever you're sending stuff to Ethereum, it's also this other model is used. I just want to make it clear that even though we call it a teleport, maybe some other ecosystems call teleports the whole thing. We divide it into 2 problems, and when we see into 2 solutions, and when we see the other solution, it will probably be clear, like in the other solution, there's no trust, or there's less trust assumptions like this one. There's a lecture on these two types in the future, though. So let me continue, maybe, and then we can talk about questions, or maybe on the following lecture. So reserve asset deposited. Right now, I'm just presenting instructions, right? So this reserve asset deposited instruction points to the second way of doing cross-chain transfers, which is called reserve asset transfers. This tells you, hey, someone moved some tokens to my sovereign account, but go ahead and mint some derivative tokens because you have some balance. I know right now this maybe doesn't mean much because we haven't talked about those two ways of doing cross-chain transfers yet in deep. But this is just another instruction to do cross-chain transfers, which is, and this instruction wouldn't be used by a regular user, right? This is sent by the system. The system cannot be allowed to just say this. And if just a regular user says this, then the chain that it's running on should fail because it doesn't have enough privileges to tell me this. So for example, Asset Hub, the Asset Hub root does have privileges to tell me that it moved stuff to my sovereign account and I should mint some derivatives. We'll talk about this more later. But a regular like Alice on Asset Hub doesn't have the privileges to tell me that, right? So that is all taken into account. We will look at it later how. Let's look at more examples. And then, so I've been talking for a while, you've been listening for a while. Thank you for all your attention. And then let's go with a few more examples and you can go to the break. There's a query response instruction, which will allow you to send a response back. So if you want to do a transfer and then report back the success or failure of the transfer, you just use this instruction. You just put this instruction in your message, and it will mean a response. No, this is the response itself. Okay, but there are some instructions that allow you to send the message back, and that message that you send back is this query response, or has this query response instruction in them, which has a response type that will tell you what you want to know. If you want to know, like, if your execution was successful, you will see it there. Good, and now we have, that is locations, assets, and instructions. So locations was sort of the bigger part of all of this, because I know they're like a new concept, but they basically act like a URL or a file system for blockchains. So it's not a file system for blockchains, but it's like the way to reference different blockchains. Then we have assets. You can reference any token you want. You can reference any asset you want. You can reference DOT. You can reference USDT, USDC, MITH, like Parachain native tokens, ETH, so no tokens from another place because you have locations. And then we looked at a couple of instruction examples. And now, if we have some questions, I'm happy to answer them. So go ahead.
Yeah, my question is about the instruction example. Is it predefined, or I'm the one who write whatever? The example, like the previous slides, there are some kind of example for the instruction. Is it predefined by the system itself, expecting across the parachains? Like if I have XMC enabled, I'm expecting these kind of functions? Yeah,
you are expecting these instructions. Like, you know the encodings of the messages that come in, and you know the instructions. You do need to interpret them yourself. But the instructions are there. There's a set of instructions,
but
and we
I
add
cannot
them.
do my own instruction?
You cannot do your own instruction. You can create, if you want, an RFC for your own instruction. The thing is, XCM is meant to standardize what it can be done. So you cannot just create your own instructions, because then everyone will just start speaking a different language. So we all need to standardize and agree on some set of instructions. That does make XCM go slower than if you just did your own thing, which is good. I mean, it's one of the trade-offs of standardizing. But if you have a use case, or if you have some operation that you think is general enough and it should be there, for example, I don't know, vote, some instruction called vote that we do not have right now, that allows a chain, like someone from any chain, to vote with tokens or with anything on some other chain, then you can propose an RFC, and there could be discussions and so on, and it will be integrated in a future version. Now, if you want to do like your own instruction, there is an instruction called transact, which we'll talk about later, which is sort of an escape hatch to this standardization of
So
things.
enable like arbitrary call, whatever it's inside it.
So transact just takes bytes, and then it's up to the system how it interprets those bytes. And it's kind of the native native transactions that I said before, in the bytes you could have just a regular call, right? Well, actually we transact is for having calls, so you can create whatever call you want, and then in transact you call it, or you dispatch it, and that will allow you to, like, if you just want to talk to another chain, just want to do a cross-chain scenario, and the instruction is not there yet, or it won't ever be there, you just want it between the two of you, you can just talk amongst yourself, create like create some sort of standard between yourselves, and then use transact for it. That's what we expect. We expect people to use transact for everything that is not yet a standard, and then if something is enough of a standard, then they could always create an RFC to make a standardized instruction, and that would have its benefits, because when something is an instruction that is standardized, then you can send it to multiple chains, and you don't no longer need to think about how those chains are implemented. They need to make sure that they have everything fixed for you. A question in the front?
On the last instruction that you showed, which was query response, how does that get triggered? Do the other instructions have a flag to say, I would like a response?
Yeah, no, there's a bunch of instructions that trigger a response, yeah. So for example, when you execute something with a transact, the result of the transact will be stored on a flag, on a register, like on a variable. And then when you do report error, it will send the response back saying whether there was an error or not, and with the value. So that's how it will work. Good. So I think the last slides, it's just there's a workshop, but that will be on the afternoon. So we will be playing around with this with these primitives. And then the next steps is, okay, now we need to know, now that we know the primitives, locations, instructions, and assets, we're not actually doing anything. Like, we're still not doing anything. We just have the building blocks. And now on the next lecture, which will be after the break, we will see how these are actually used. The break is at 10, right? Okay, good. So we're done for now. We have 3 minutes early. Okay. Oh, there's one question, sorry. Last question then, maybe, if it's fast. If it's not fast.
Hey, Rodrigo here. I still do not understand the full difference between XCM and the protocols that it's using, and the network protocols that the node uses to communicate with other nodes. Because as far as I understand, blockchain nodes require like both UDP and TCP protocols to communicate each other, connect each other, and establish secure connections and frame specific messages to allow this. But that's like on the node side, right?
That's on the node side, yeah.
So if we do have that, why is the XCM need, or is it like now layer above the network layer?
It is.
And it uses another protocol layers to enable this communication that also uses all the other protocols?
So I talk about protocols the same way that people in blockchain talk about protocols, but I mean, they kind of are networking protocols. But for messaging protocols, we're not talking about networking protocols between two machines like TCP and UDP. We're talking about messaging protocols between two chains. So we cannot, how the machines that have those chains communicate between each other is via UDP or TCP or I don't know, whatever they want. Like quick, I guess, but anything they want. But this is a protocol between two chains, not between the machines themselves. So we need a protocol to like actually make things go from one place to the other that takes into account the fact that a chain is a collection of multiple nodes. It cannot be a protocol between two machines. It needs to be a protocol between two networks. In order to do a protocol between networks, the UDP or like HRMP, for example, it has to do with, in Elves and Polkadot, has to do with the collators, which are a group of people, and the collators are supposed to grab the message and put it in a message queue which is part of the runtime, and then the collators from the validators ensure that, and then the collators from the other chain get it. Like, it's a protocol that involves a lot of machines. It's not just a networking protocol. Okay, so that was the last question, and we go out to the break. Thank you.
Figure out what the problem was? Oh, I mean, yeah. They say you're okay. Now? Okay, focus.
Hello, hello. Yeah, nice. Okay, so welcome back. I hope you had a nice little break. Let's keep on talking about XCM, cross-consensus transfers. Okay, so we have now until 12:30, is it? Yeah, I think so. It's 2 more hours. And I have the same amount of content, I believe. Then we have lunch. And then in the afternoon, just as a reminder, we will be going through hands-on exercises for all of this. So I know this is very much like a huge block of like knowledge that might seem very specific, might seem like, why do I need this? And then we do a hands-on exercise, which will show you actually working. And then you will have a mocked environment where you will have 2 chains, and you will be able to send funds from one chain to another and do cross-chain things, and you will kind of understand that this works in the wild and why you're learning about it. Okay. So first I want to talk about cross-consensus transfers, which should really be called cross-chain transfers at this point, even though XCM is, it technically stands for cross-consensus messaging. Yeah, cross-chain transfers because you want to transfer between chains. It should probably be called cross-chain transfers. So I wanted to talk about this specifically. So this is another kind of mini lecture specific on this topic. Because yeah, I think it's different from what other ecosystems do or use or how they frame it. So we have 2 ways of doing cross-chain transfers. This should really say cross-chain. We have 2 ways of doing cross-chain transfers. So the first one is asset teleportation, and it works by burning the assets on the source and minting them on the destination. This method is the simplest one, but requires a lot of trust, since failure to burn or mint on either side will affect the total issuance. So yeah, we could do a teleport where we check that we actually do burn and we actually do mint, but we really do have another name for it, which is the second variant. Teleports are just when you really you're the same team or you trust the system, so you just do teleports. But we'll talk about the second approach, which is the one that's mostly used on other scenarios that are not those ones. So in this case, you have one example, which is system parachain. So Bridge Hub trusts Asset Hub because the developers are the same. So we know that if there's a bug in the code. It's not that someone was malicious. So we can use teleports between them. You can teleport dot between all of the system chains. And that what it allows, you just do teleports between system chains. But for example, you cannot do a teleport of dot from Polkadot to Kusama. So what we usually say is if your asset is teleportable to another chain, you're basically part of the same thing, right? If you between Bridge Hub and Asset Hub, they're all part of the reserves for DOT. They're the owners of DOT, right? If you teleport something somewhere, both of you are the owner, right? Both of you are accounting and both of you are the bank. Like both of you are the owners of the token. That's kind of the way you should be framing it. So whenever you teleport something, you're sharing or you're implying that the other side is also an owner of your token. Like also an owner. So Bridge Hub and Asset Hub, all good. Polkadot Kusama, no teleports. And there are other cases, which I didn't add here, but there you will see it on the assignment, which we will release on the afternoon, which is a parachain can choose to trust Asset Hub as the like co-owner of their parachain token, and that way they can just do teleports between themselves because they know that the Asset Hub is like a trusted system. If Asset Hub was malicious, they would be screwed anyway. So they inherit the trust from the fact that Asset Hub is part of the system. When I say you trust Asset Hub, is like you also trust, for example, every parachain trusts the code of the relay chain. Because if the code of the relay chain was wrong, then yeah, you could break every parachain you wanted to. So they trust the relay. And now we move on to another mechanism, which I think it's like the better way to think about things. I think teleports is more of a edge case, right? That we use with system parachains, kind of specifically. But reserve asset transfers is kind of like the way you would do things. So what you would do is you have a chain R, or this is, I mean, it's not necessarily the way to do things in general. It's just the way we do things in Polkadot because we found it to be extremely, extremely helpful. We have two chains, A and B, and they don't trust each other. And we have one chain R, which is the reserve. The reserve is the issuer of the token, the one that everyone has to trust, right? If we are dealing with USDT, we trust the issuer, which is Tether. If we're dealing with US dollars, we trust the US government because it's the issuer. At any point in time, let's say, they could increase the issuance and take value from our tokens, right? Like we're always trusting the issuer of a token when we use the token. Same with like scams and meme coins. Like if you are dealing with a meme coin, you know the issuer of the meme coin or the owner. Maybe it doesn't have an owner like we have. Of course, you could do it in a way where no one has the control. But if someone has the control, even if it's not one person, even if it's a team, even if there's a governance, you're trusting that governance system to be like sane, like to not change all the time, to not be malicious and want to break the economics of the token. There are a bunch of trust assumptions on the issuer of a token. When you're using DOT, you're trusting the DOT governance, you're trusting the validators, you're trusting all of the tech behind it, right? You're trusting there are no bugs in there. When you're dealing with ETH, the same thing. You're trusting in Ethereum, in all their system, in their governance and so on. So that's just one thing about token issuers. So when you want to send a message from A to B, and there's a chain R, which is the issuer of the token generally, then what you want to do is A has some derivatives of the token. They don't have the real token. The real token exists on the reserve. A has some derivatives of the token. It will burn them. It will tell the reserve, hey, I have burned my derivatives. Yeah, this actually, it doesn't start from here, so let's start from the reserve. So the reserve has a sovereign account for both A and B. Hopefully, sovereign accounts, all good. So it's an account, the chain R will have an account owned by A and an account owned by B. And A presumably starts with some amount of tokens in their sovereign account. So when A has those tokens in their sovereign account on R, R will tell A to mint derivatives to match what they have on their sovereign account. Sort of to mint something that matches one-to-one to what they have on their sovereign account. So we have that A has some tokens in their sovereign account on R. And now we do start the flow. So A will burn some of the derivatives. We'll tell R, hey, please move my tokens from my sovereign account on A to B's sovereign account. And then please forward a message to B telling it what happened and making it mint the new derivatives. Here A and B are only trusting the reserve R. Now let's look at some examples. So, yeah, and this works also with R being either A or B. And when that happens, we have like what will be like a regular or what you might expect from a teleport. So let's say A is equal to the reserve. So then we only have A and B, right? So A is both the sender, but it's also the reserve. So then we have like some sender account will move X of the real asset to B's sovereign account. And then a message will be sent to B. Here I managed to make arrows work. We'll send a message to B telling to mint X derivatives. That would be how that thing works. And then we have another example, which is, for example, Polkadot to Kusama, which I told you that it's not a case where you want to use a teleport. So in that case, you have Polkadot, for example, and you have asset hub Polkadot, and you can have a sender move X of the real dot to Kusama's sovereign account, and then send a message to Kusama via the Polkadot Kusama bridge that it should mint X dot derivatives. So this is how it works right now. And this is because Polkadot is the reserve for dot, and it will just move dot to the sovereign account of Kusama and tell Kusama, hey, you have some funds on your sovereign account. And that's the two examples that I had. Yeah, there's a question down at the back. Yeah, not working mic. Both are dead.
I have one. Test, test.
Okay, the one on the front works.
Yeah, it
okay.
works now. Okay.
There's so many mics.
I got 3. Okay, like when we have the example for the reserve chain, are we talking about like something similar to the Circle CCTP where the reserve chain is minting actual token in the destination chain, or we are just like doing kind of like a wrap token and then like minting and printing based on like the methodology we're using?
Yeah, so it's actually, it's closer to the second than to the first, I believe, if I understood correctly. So the reserve is a chain which owns the token. It's kind of the issuer of the token or the creator of the token. And what it does is the real tokens, of course, they do not go away from that chain. Like the real tokens exist on that chain. And then whenever two different chains want to interact with that token, they just tell the reserve to move stuff around from one sovereign account to another, right? So the reserve keeps account of all of the sovereign accounts. So if you look at only Asset Hub, for example, because Asset Hub is the reserve for DOT and for a bunch of other things. So if you want to know, well, right now we're doing the Asset Hub migration, so the reserve would be the relay chain. But if you look at the reserve for DOT, and you look at all of the sovereign accounts, you can find out how much DOT is in every parachain. But all of that DOT that is in every parachain is actually backed by a sovereign, by some tokens in the sovereign account on the relay, on the reserve. Yeah.
Looking at the statement of trusting the reserve,
yep.
How does that align with the trustless and decentralized concepts of Web3?
Yeah. So we're using the word trust, and every time we say the word trust, people get this skeptical. Maybe we should change it, but no. Like trust is a good thing and the thing that is needed. So I always say the slogan "Less trust, more truth" should actually be less blind trust, more verifiable truth. So when you say trusting here, it's like you're always trusting the issuer of the token. And trust, I don't mean trust in one person or trust in one institution, which is what we usually talk about when we say trust in Web3, is we don't want to blindly trust Meta, for example, or we don't want to blindly trust Amazon. But we do have to kind of know or agree or trust that a particular governance system in a network of decentralized entities is sane, right? Like it could always be a network that has a broken governance system. And so that's where we wouldn't trust that network, we would trust another network, for example, right? Like Polkadot has a lot of validators and it has a lot, like the good security audits, for example, and good governance. But you wouldn't, if someone launched a chain right now, you wouldn't expect the same level of guarantees from that chain, right? It's just a matter of like the guarantees that you, or the things that you expect. So here, the crucial thing, I believe, is you are always trusting the issuer of the token, or not necessarily the issuer, but the one that can govern tokens. So you're always trusting some governance system in this case. If you don't have on-chain governance, or if you have a token which doesn't have any sort of governance, like for example, for Bitcoin, then maybe, yeah, you don't need to trust any sort of, like no one on Bitcoin will be able to mint more than the total supply, for example. But you're still trusting that the Bitcoin system works, right? You still, if there's a bug in Bitcoin, you're still trusting that. So,
just a follow-up on that. When we say mint happens by the governance systems, is it kind of a centralized, or is it again how much to mint, what to mint would be on a consensus, and
sorry, can you repeat that again?
When the reserve mints
Yep.
more,
Mm.
would that whole minting concept be, would it be centralized, or would it be again put up for a thought, and then based on the consensus, there'll be decision taken to say that yes, we'll mint so much?
Yeah, so it's not by a when I say mint, I don't mean by a centralized party. And even like R doesn't even mint, so R just moves stuff around, which is fair. Like it's moving stuff from one, and it's not even R that is moving it like on its own, which is the chain anyway. But it's the chain A, the root of chain A. So probably either the pseudo root, if they're like a permissioned chain and there's a pseudo account, or a governance system on A decides. No, sorry, that doesn't need to be the governance system. But A sends a message to R. And then R just completes the expectation of A, which is to move funds from A to B, like from the sovereign account of A to sovereign account of B. And then it tells B to mint tokens. Now, when B gets a message and it tells it to mint tokens, it's just part of the protocol that when it receives the message from the reserve of a particular asset, then it's allowed to automatically and like permissionlessly mint derivatives for that token. So it's all happening automatically. There's no one in the middle saying, okay, I'm going to mint, I'm going to burn. It's just A burns the token as well. And the burning is not done by one person. I mean, of course, if there's a user on A, Alice can choose to call, so taking it more to the concrete world of frame that you saw before, A might call an extrinsic, or might submit an extrinsic so Alice might submit an extrinsic on A that burns the tokens that Alice specifies, sends a message on behalf of the whole chain saying, please move this little bit of tokens from my sovereign account to B's sovereign account, and then please forward another message to B. B would automatically receive the message and know, like in the code, there would be some logic for automatically minting the derivatives. And then the rest of the message that Alice or that chain A sent would be, please deposit it on Bob or whatever.
Sorry, another follow-up.
Sorry, it was too long, maybe the
no worries.
chain of actions.
Coming from the Web2 world, again, these kind of questions do come across to me. If we burn first and then ask to transfer, is it guaranteed that the transfer will happen? Or if the transfer fails in any ways, then would it come back and would I mint on my side again?
Yeah, so we actually, because of this, we moved this logic of burning and sending into its own instruction called initiate transfer. So the only thing you do on A is execute an XCM, a local XCM, because you can also execute XCMs locally. They don't need to be messages. That's why XCM programs is maybe a better term. You execute it locally, and there's an instruction called initiate transfer that when it gets executed, it will burn and send, and if the burn fails, everything fails, right? It's like an atomic thing. So there's an atomic step to go from A to R, then R moves the things also in an atomic way, and then sends a message to B, which also in an atomic way receives it and mints. And if at any point there's an error, if there's an error in A, the user just gets an error and nothing is wrong. If there's a problem in R or B, the assets will get trapped. And A would need to send another message with an instruction called claim asset, which would claim the trapped assets. So that's how we handle like reverts, which was something that someone asked as well before. Which is like, there's no way we can automatically send it back, because was it now the sending back also fails. Like it's a complicated operation that we maybe cannot revert. So we just leave stuff locally, and someone needs to go ahead and claim them. And that's something that maybe has a slide on it, maybe not, but we can of course like talk about it afterwards. Okay, so this is the case where the reserve is the sender. So this could be the case where there are two parachains on Polkadot. One has a token, like token A, and the other one is parachain B, has a token B. And so A wants to send to B. So what it can do is to just say, okay, I'm going to get a sovereign account for B. I'm going to give it some funds. And then I'm going to just send it, okay, you have your tokens. Please create some derivatives. So if we want to give them a name, those would be like wrapped derivatives or whatever, like wrapped dot, let's say, or wrapped A. And they would represent and map one-to-one with the real thing. But of course, the real thing is in the real chain. But they can always know, like B can always know, or let's say B mints, like the system, B has a bug and mints a lot of that token. It doesn't matter because the truth sits here. And that's the thing with trust. Like A doesn't care about B's code. A only cares about its code, and its governance, and it's all of the things. So if B has a faulty governance or a malicious attacker like captures the system and mints 1,000,000 dot, for example, then it doesn't matter because it's not minting real dot. It's minting a derivative, but then anyone can see, like the system can see that it doesn't match what it has on its sovereign account. So that's why it's not real, and then it starts being like not worth the same as a dot. This is an example, Polkadot Kusama, the same thing. So Polkadot doesn't care if Kusama doesn't do things right. It only cares that it moved things to Kusama sovereign account. Good, and now we have an example with images that now do work because I'm on localhost. For an example transfer between two chains. And we will try to talk about all of the things that we talked about on last lecture. Right? We will try to mention, okay, where are locations being used here? Where are assets used here? Which instructions might be used here? Is this like a cross-chain transfer of some sort? So this is the example that we had before. If you remember, we will keep on going through and through this example, dissecting the different steps as we go, or to a different level of depth every time that we move on with the lectures. So now we know, talking about location specifically, now we know that Alice would specify the destination as a sibling parachain. A destination as I go to the relay and I go to parachain. Just a way to reference the parachain that I call the para. So there's asset hub and para. This is how they would specify it. Now, someone asked me on the break, like, do I need to specify locations? Like I mentioned, we don't expect like users of Polkadot to know about locations. We expect it to be a detail of the system. So the idea here is you can either create an extrinsic, like a call on your pallets, because you know a lot about frame. You can create a call on your pallets that doesn't take a location as a parameter. It takes like a para ID, for example, and then it will grab that para ID, which will be here, and it will append, it will prepend. You need to go up and then you go to the parachain. But even better than that, you can make an off-chain library, or you can make a UI, like the actual thing that a user interacts with, can abstract away the locations and just make sure you go from where you want to go. Like that's even not what you want. What you want at the end of the day for the user, so this is like a parenthesis for user experience on Polkadot. A user shouldn't even know that there are chains, like there are multiple chains on the back end. They should just be using an application. So they use an application that maybe does some swaps, right? And they don't care if the swaps are happening on hydration or on Asset Hub. They just use the application and they just click a bunch of buttons and select and everything is fine. Now, behind the scenes, the off-chain library can call XCM all the time, keep account of how much tokens they have on one chain, they have on another chain. If they want to do an action, if the user wants to do an action that is not on like the chain that is supposed, sorry, if the user wants to do an action and they don't have enough balance on that chain, the app could, behind the scenes, move balance from one chain to another and do the action. So all of these things that I'm talking about don't mean that the user experience is dictated by this. Like you shouldn't copy the backend and make that the front end. You should abstract as much as you can on the front end. The same thing with palettes. Like in palettes, we mentioned that, of course, if you create a call, it's callable from the outside world, but you shouldn't create like one call that does a bunch of things because it would be nicer for the user. You would expect the off-chain library to call, like to batch multiple calls at the same time. You need to deal with this on the front-end level. Okay, parenthesis done. Unfortunately, like lots of people don't understand this and just copy and paste like palette calls. And then you go to an app and instead of having a nice experience, you have like a list of which extrinsic you want to call and you don't know which order you should call them. And it should all be abstracted away. That's end of parentheses because we should improve on that. Okay, so that's how you specify the destination with all of these parentheses that it should be handled by the front end. But the front end specifies a location, for example. You can do the parents one and then junction parachain. Then a transfer is made from Asset Hub to Para of, for example, 5 DOT and 10 USDT. Then Para will see the origin, so the origin of the message, as /asset hub. And it will see it as the actual origin of the message. And it will see that the beneficiary is Bob. And we will look more into this later, how it will see that the beneficiary is Bob. And then we'll send the funds to Bob. So this is about the locations. Now we can talk about assets, right? So in this same example, how are these assets represented? As we saw, asset IDs are represented by locations. So the asset of dot is just parents, 1, right? The asset dot is represented by the location of the network, like of the top of the network, which in this case is the relay chain. So here we're sending 5 dot. We just specify that we're using dot. This is parents 1, interior here, or in this notation, just dot dot slash. So go up a bit, that's dot. And then the second one is USDT. What we have with USDT is some convention that we created, which is palette instance 50 is the palette assets on Asset Hub. So just have the convention that because anyone can create an asset on Asset Hub, we will put all those assets inside of palette instance 50. And then general index is the index or the ID of the assets, because in Asset Hub, anyone can create assets with a numeric ID. So in here, I just know that the ID for USDT is 1984. So that's how you would do it. Then instructions. Let's do a simple version first. The instructions would really be as simple as, hey, receive 5 dot, because I'm on Asset Hub, I moved stuff from the sovereign account to another sovereign account. So the instructions are, hey, receive 5 dot, receive 10 USDT, and deposit all to Bob. That's fairly understandable, right? Now, actually, what happens is something more complicated, but not that much. I mean, the names of the instructions, I took the liberty of changing them to the actual name, which is quite, I mean, receive might be better, but this is reserve asset deposited. This means we're doing a reserve transfer. You got deposited some amount of funds. So yeah, reserve asset deposited, reserve asset deposited, deposit asset all to Bob. That didn't change too much. But then we do have an instruction called pay fees, which makes sure that fees will be paid and lets you specify how much you're willing to use for fees. For those of you who know, about smart contracts, it would be kind of like choosing the estimation of the weight. So you can choose how much you want to use for fees. If it's not enough, you will get an error. If it's enough, all good. And why do we have it? Because we can, with this system, we can allow particular origins to not pay for fees, for example. So we can allow the root of asset hub to not pay fees on your chain, for example. Or we can allow different things to not pay for fees by just not specifying pay fees. And then we have this clear origin instruction, which would clear the origin that you saw before. The origin was asset hub. So this clear origin instruction says the origin from now onwards will be none. And then you just deposit all the assets above. Why do we have this instruction? Because as you see, this instruction seems to be pretty permissioned, right? Like no one, or not anyone, for example, especially not Alice, which we don't know who she is, can tell the parachain, hey, just mint some 5 dots, right? Like it seems weird if Alice would be able to do that. So this instruction will actually fail if the origin is not the root of asset hub. And that's where trust comes in. Like this chain para is configured so that this instruction will work if the sender is asset hub. But it will not work if the sender is Alice. So what we do is when Alice sends a message, we actually have asset hub send a message, execute the permissioned instructions, like please mint 5 dot, please pay the fees, please mint 10 dot, and then we clear the origin so that it's left with nothing. And then here we just have access to all of the tokens that we've minted, but we don't have access to, for example, Asset Hub's sovereign account or to, yeah, basically Asset Hub's sovereign account, else Alice would be able to do a withdraw asset and take everything from Asset Hub, which would be bad. So we just have a clear origin there for making this work. But the idea is mint some dot, mint some USDT, deposit all to Bob. And we just add pay some fees and clear the origin because of permission reasons. Okay. And that is the example of a cross-chain transfer. And as you see, it's just using the second model, which is the reserve asset transfer, which is used whenever any parachain is involved that is not a system parachain. You can use that model, and it uses this reserve asset deposited, and it just works. Like if you execute a cross-chain transfer right now on Polkadot from like Asset Hub to another chain with 5 dot and 10 USDT, it will work, and it will work in this way. So there's a question down there at the back.
Yeah, 2 questions. The first one, if you go back to the slide with the pay fees, is this fees like for the compute, like the weight you are using, or for providing the assets?
It's fees for the weight. Yeah. So just like in Frame, you need to pay fees for weight.
Is the source and destination, or only the destination?
Only destination. So, or it can be source, but it's wherever this is executed, that's where you need to pay for fees. Yeah.
When is my second question. When I'm doing like kind of cross-chain to transfer assets, here I'm talking about like providing the functionality to the end user. Having asset hub in the middle will increase the security, but I'm not sure it will also increase the cost for the end user, because like we are like, I think we are using more resources.
Yeah. So agreed, but it's kind of the way to go. So I actually don't have this in the slides, but there's a very good, so we do have is it the Parity YouTube channel or Polkadot? I think it might be the Parity YouTube channel, which has a playlist on Asset Hub itself, like just talking about Asset Hub and why it exists and all those things. And it is a central entry point to the ecosystem. One of the main reasons we have it is for integration with centralized exchanges. So a centralized exchange doesn't want to integrate with a million chains. Even if the integration might be easier, maybe, they don't want to integrate with a million chains. So what we do is we allow every parachain that wants its native asset listed on a SEX, on a centralized exchange, they just will register the asset as a foreign asset on Asset Hub, and then the centralized exchange will be able to know about all of the assets in Polkadot by just looking at one chain. And that is very, very useful. And then whenever you want to move any sort of fund from parachain A to parachain B, you do go through Asset Hub most of the time if you want to use DOT or USDT or any other parachain token. But you have access to all of the tokens in the ecosystem, which is very beneficial. Because if not, we do require a channel as well between two chains to communicate between each other. And if now with Asset Hub, every chain has a channel with Asset Hub, but not every chain has a channel with every other chain. So yes, it's more costly in some ways, but it really is a very good solution to having access to all of the assets, to not having to create a channel for all of them, not having to configure it for all of them, so on. Yeah.
One last question.
Yeah.
Is it enabled, like, or I can do transfer assets using the Asset Hub and in the same transaction passing arbitrary messages?
Yes. So you can do multiple things. So here,
In the same transaction, I mean.
in the same message, yeah.
Yeah.
Yes. So in the same XCM, so here we see 5 instructions. So in theory, okay, well, all of them kind of reduce themselves to one action, which is just like putting funds in Bob's account. But in the middle, you could have like an exchange asset instruction, which would swap DOT for another thing. Or you could have a transact instruction that would execute some code, and then you can have like a report error instruction that would send a message back with the result of the call to know, for the sender to know if it was successful or not. So you can add more things. And in the exercise that we do in the afternoon, we will see an example of, so this is not the example that is here, but imagine this is like a DEX chain, right? So we'll see an example of writing a message here, having the user, I mean, the user would only sign one extrinsic. But in your code, you will see you create a message that tells it to come back. So you will make a message that goes to the DEX chain, does a swap, and then returns.
Like ping pong.
Yeah, exactly. And there's also a ping pong example that you can configure it to go like 10 times, 20 times, and it will just keep on going until there's enough fees. Yeah, exactly. So that's really, I think that's something really, really cool that you can nest XCMs. So yeah, to do that, you need to nest XCMs, and you can nest them. And that's, I think that's a very cool thing. Not only for the swap and come back, also for if you want to like get a lot of assets along the way, you can send a message, get some assets, then forward it, get some assets, forward it, do the swap, come back, for example. Okay, so now that we're done with this, then now let's look at the meat of XCM. So yeah, we have talked 2 hours already about things that are not execution. Now we will go into how XCM is actually executed, which is really the meat of everything, right? How do we interpret the instructions? That's the meat of everything. Good. So from now until lunch, we will learn how the XCVM works, which is a cross-consensus virtual machine. We will just call it the XCM executor, which is, yeah, and then the XCM executor, which is an implementation of the virtual machine. So at the core of XCM lies the cross-consensus virtual machine, which is the XCVM. This is a state machine that is where state is kept track in registers, and how the virtual machine should act is written in the XCM specification. So if you go to the XCM specification, you will see something about locations, something about assets, all of the instructions that are available and how what they mean, like what are the semantics of each instruction. But you will also see registers for the machine, like what they're supposed to do, and you will see the semantics of the instructions in terms of those registers. So the virtual machine is the thing that's supposed to take a message and execute it bit by bit, interpret each instruction, and change internal state or change system state based on it. So it has registers like, and these registers can be modified by the instructions. So it has registers like the holding register, which holds assets that are in holding of the execution of the machine, of the XCM. It has the origin register, which just stores where the message came from, and it stores it because you can clear it, you can modify it via instructions based on the semantics of the instructions. You have fees. There's a fees register, so that whenever someone says pay fees, they take it from the holding and just put it in the fees register to know that that's the pot that they can use for fees. You have an error handler. In case an error happens, you can send a message somewhere, and there's an appendix that's like, no matter what happens, always send a message somewhere, or always do extra work. Yeah, so the origin register contains an option because there might be no origin if you clear it. So the origin can be mutated by different instructions. You can clear it. Then the holding register is the most important one, is the one that holds a number of assets. It expresses a number of assets in control of the execution that have no on-chain representation. So whenever an asset is withdrawn, it is actually burned on the chain, and it exists on the holding register. Now, during the execution of the XCM, it will be eventually deposited somewhere, and then it will be minted again. So it will look like it was a transfer, but it actually was like a burn from the chain itself and into the executor, and then it was a mint back into the account. And then, of course, if the execution ends and you didn't deposit it anywhere, they get trapped. They don't belong to any accounts, or as well, they don't belong to any account. So it doesn't matter where. What's sorry?
Please just confirm this. I just missed it. If I allocate some of the assets and I don't deposit them somewhere else, they are not like reverted or anything, not automatically at least.
I mean, they could be reverted. It all depends on Frame. You know that Frame has transactional layers, right? So if there was an error locally, Frame will make sure that it's rolled back. But if there's an error on another place, they will get trapped, and you will need to make a subsequent message to claim them. Okay? That's the error handling thing. But I mean, this is just like a distinction between the chain and the executor. So they don't belong to any account. It doesn't matter where they came from. For example, you can have a message that does withdraw asset, withdraw asset, withdraw asset, and it will withdraw from 3 different accounts. I mean, you need to modify the origin so that they come from different accounts. But at the end of the day, they all get put in this holding register, and it doesn't matter where they came from when they are here. And it can be seen as a register holding unspent assets that you will presumably spend during the execution of the XCM. The fees register is just holds assets destined for fee payment. So whatever is in the fees register will be 100% destined for fee payment. But then, of course, there's a way to you already paid for everything and you want to take stuff away and then back into the holding register, you can. And then now that we talked about this, instructions might change a register, the state of the system, or both. So you can imagine the withdraw asset instruction will change the state of the system, will take assets from an account, and it will change the state of a register. It will put assets into the register. Then deposit will do the same, but there are instructions like clear origin, which we saw, which only changes registers, doesn't change the state of the system. And there might be instructions which only change the state of the system, not the registers. So that's everything that an instruction can do, is those two things, either remove a register or the state or both. And now we'll see an example of an XCVM in operation. Oh, first we'll talk a little bit about it. So it's just a virtual machine that executes in a typical fetch execute loop. Each instruction is fetched and executed in order. And two additions are the error handler and appendix. They contain more instructions that are executed if there's an error, or unconditionally at the end of execution accordingly. These are sort of, there's an instruction called set error handler, which you can use with a nested XCM. And then if there's an error anywhere in the execution, it will go to the handler. And then there's the appendix. There's also an instruction called set appendix, which if at the end of the execution, unconditionally, the appendix will be called. You can think of it as a try, catch, except, no, sorry, a try, catch, finally block in programming languages. Okay, and now that we talked about the XCVM, which is the specification of a virtual machine, we will go to the more practical side of things and talk about the XCM executor. So the XCM executor is the parities implementation of the XCVM spec, and it's the entry point for executing XCMs. So while you might implement your own, or where you might make your own implementation of the XCVM specification, we provide one called XCM executor, which is on the Polka.SDK repo, and it's built in Rust, and you can take a look at it and see how it processes each instructions. So again, the XCM executor is the entry point for XCM, and it's the one that has to actually interpret all of the instructions and holds the registers and so on. So this here is how we would call the XCM executor in Rust. So we would do XCM executor, which is just a type, as you're very familiar with right now. We use types a lot. So the XCM executor has this function called prepare and execute, which takes an origin. So as we see here, we do have an origin. This is where it comes from. So you're in frame or in code itself, you can choose where the message came from. The system that we use will make sure that the origin comes from the transport protocol, right? And it's a correct origin. But in your mocks, you can always, like, I don't know, when you call prepare and execute directly, which is a very low level API, you can put any origin you want. And then you put the actual program, the XCM. Then you have some hash, a wait limit, and a wait credit. And note on configuration. So the XCM executor is highly configurable. So it can be implemented by many different chains, right? Because we need different chains to interpret instructions in different ways. But just adjusting some configuration items. So we don't need every chain to implement their own specification of the XCVM in order for them to interpret instructions in different ways, right? Because you might imagine different chains interpret instructions in different ways. There could be a chain that is not a DEX, doesn't have a DEX. So the swap instruction, the exchange asset instruction, they literally just throw an error. Now we don't need them to implement their whole thing with like registers and so on, just for changing that behavior. So what we do is the XCM executor, which will take a little tour after the lecture, after the slides, is a Rust, right? Which has all the things. It's highly configurable, just like frame palettes are, so that each chain can configure it in the way they want to interpret instructions the way they want. These items provide the executor access to the chain's runtime. So this, you can also think about this as host functions that let the executor call into the runtime the same way that pallets have a config trait, which lets pallets call into runtime things. XCM has a configuration which lets the XCM executor access runtime things. For example, this is the way you allow the withdraw asset instruction to actually go to the state and take funds out of the state. So the XCM executor doesn't know anything about state. It just knows that it has an interface that you use to interface with the runtime, and it will use that to take stuff from the state. And this is also how different chains can route different asset instructions to different pallets. So what if one chain is using pallet balances and another chain is using pallet assets? They both need, both of these pallets are standardized in the withdraw asset and deposit asset instructions, which is what we talked about before. XCM is a standardization of the functionality that you want to do on a chain. So it doesn't matter if you have one pallet or the other. It doesn't even matter if you have both, and they depend on, it depends on the asset ID if you use one or the other. All of these implementation details, you would configure them on your runtime, and then from the outside world, we would just use instructions. Like from other chains, we would just use instructions, and this configuration would help you route the instruction to the actual implementation detail, the actual entry in the database, right? Yeah, I have a question over there.
Okay, just to to clarify one point, when we say executor, are we talking about like another job the validator or the collateral is doing, or it's a standalone kind of stakeholder?
The executor is just, yeah, my bad, because executor sounds like it's an actor. The executor is a struct, like a Rust struct. We call it the XCM executor, but it's a Rust struct.
Like who's running this job, like the collateral or the provider?
What's the
Who's running the kind of like the checks, the
yeah. What were the two words you mentioned?
like who like
okay, now don't worry.
which actor in the Polkadot?
Okay, yeah, okay. So the collator of the validator, I guess, or something. Okay, so the full node, just like the full node would execute every call on a frame pallet, we will see there's a pallet called pallet XCM, which like imports all of the Rust things from XCM and executes them. So when I mentioned this is just the Rust code, right? And this Rust code can either be used on a regular script on your computer. It wouldn't make much sense. I mean, because it's not very useful on its own. But we do have a pallet which will call this. And so who is executing the pallet code? It's the full node. So it's either a validator or a collator or just a random guy that wanted to run a full node. Yeah, those are the actors. So yeah, there might be a misnomer for the XCM executor. It's just the code that executes things. It's not the actor. Yeah, okay. Good question, because I didn't realize the name could be confusing. Okay, and this is another important thing. Different chains in the ecosystem might use different pallets for the same things. So we need them, or in a runtime upgrade, they could change the pallets. And this here, this configuration, is where if you do a runtime upgrade, it's your responsibility to make sure that the API, which is XCM, is not broken, right? You need to make sure that the interface to other chains is not broken. That interface is XCM. Okay, so now we can continue the example, you know, the transfer from Alice to Bob, where we talked about the locations, talked about the assets, talked about the instructions. Now let's talk about how it would actually be executed. It would be executed in 2 stages. So it would be executed, there will be a local XCM executed, and then a remote one, which this kind of ties back to the, what about if you burn and then you want to send and the burning fails. So we do it as one thing. And in order to do it as one thing, we just make it its own local XCM. Because you can execute XCM programs locally. It's just a language to standardized things, but you could use them locally. So for example, the instructions of the local XCM might look a little bit different than the remote ones. You got a first one, which is withdraw, which is, here's the simple version, right? That's why I have some code, some dots. So you withdraw some 5 dot and 10 USDT. This would happen from Alice's account. So this XCM is executing with the origin of Alice. We saw that in the remote chain, we would use the origin of Asset Hub. Here, we would use the origin of Alice, right? Of the parents 0 junctions account ID Alice. So we first have a withdraw, and then we have the middle one, which will be pay fees. I'll show you later. But then we have some instruction called initiate transfer. And in here, you put the destination, which is going to be parents 1 junction parachain para. And then we will send the assets. And then we will send a bunch more information. So this is simplified, complicated. It's like this. So initiate transfer actually takes a bunch of parameters. So let's say we withdraw 0.5 dot and 10 USDT. We say 0.1 dot are destined for fees, right? And then we initiate the transfer and we say the destination, the assets, the remote fees, because we will need to pay for fees on the remote chain. And then a remote XCM. And the remote XCM is just, hey, deposit, right? And then some preserve origin false, which we'll talk what it is later. But remember, we already saw the instructions of the remote XCM, so now we can match. I mean, we can figure out what initiate transfer does. So as you see, this instruction results in a message being sent. So there can be instructions that result in a new message being sent, right? Okay, let's look at the thing executing, at the program being executed line by line. So let's say we're now the interpreter of this language. We are the XCM executor, which is just some code, right? This would be all executed in a full node. So we have the chain state on one side. So Alice might have like 100 dots, 500 USDT, 250 USDC. And we have some registers with some origin, which is Alice, the local Alice, some holding that is empty, some fees that are empty. So and on the right side, we have all the instructions with a little arrow telling us where we are executing. So we execute the first step, and now we see that we withdrew 5 dot and 10 USDT from the chain state, and we put it on this holding register, right? That those things that are now in holding, they are like unspent assets. They don't exist on the chain anymore. They're like ephemeral, and they're only tied to the execution of this particular instance of the executor. Then we say, okay, let's pay for fees. That will only move things from the, oh, did I not remove it? Yeah, okay, so we moved stuff to fees. This should have been reduced by 0.1, right? My bad on that front. Seems like at some point I didn't update the image. But so, yeah, so we set pay fees with 0.1 dot. So what will happen is from the holding, we will move 0.1 dot into fees. And this difference that you see with 0.1 is that while we are at it, we will pay for execution. So we pay for execution because we know how much an XCM program weighs because we benchmark it. So we do have benchmarking for XCM, which means benchmarking all of the instructions. And then the weight of the message is the benchmark of all of the, is the weight of all the instructions added together. So we do have a static weight that we know how much we need to pay for. So that's why, let's say the static weight costs 0.04. So that's why we get this here. Why do we have this register then? Why can't we like not have it? It's because we need to pay for delivery, which is a different fee. Whenever the initiate transfer instruction is executed, we will need to take funds from the fees register in order to pay for delivery. And there might be multiple instructions that send messages. because nothing stops you from writing a message, writing a program that does initiate transfer like 3 times and sends to 3 different places at the same time, right? That's something you can do. Usually you don't do it because you can just batch. You just batch extrinsics. But it's something you can do, and it might be useful at some point. So what you do is you move stuff to fees, and then you do an initiate transfer, which would send all of the holding here. I also the delivery fees costed only 0.04, so we're left with 0.02 at the end of this. This would get trapped because you didn't use it. There's an instruction called refund surplus that if you have a surplus of fees, you can just get it back, and then you can deposit it to your account. Like you give yourself a little refund. Here we just didn't have those instructions to make it simpler. But at this point in time, the holding is empty because we said deposit. Oh, yeah, sorry. In the assets, we didn't put anything, but in these assets, we would do something like all, right? Like take all of them. And that's why the holding is empty. And at this point in time, a message has been sent. Now, of course, sending depends on what transport protocol you're using. Usually in HRMP, sending means we just put the remote message in a queue, and then at some point it will be moved from the queue to another queue on the recipient, right? Great, and that's, and that's the local message. Yeah, there was a question over there.
Yeah, it is related to the weight, expected weight in the destination chain. Yeah, we are benchmarking our own calls, but we haven't. I don't say no idea, but I cannot trust the benchmark. It might be high or low. At the end of the day, the transaction is this actual weight. This is something also to consider. Maybe I'm putting a weight, a weight which is less or more, and then the actual weight is the resource usage. So how can I make sure the estimation of the fees are correct without relying on the developer in the parachain, the other parachain? If I'm allowing I'm transferring assets from whatever chain I'm giving this functionality, do I do my own benchmark on while I'm doing this, or what you're doing?
Yeah. So on one point, which is do I how can I not trust the developer of the chain I'm executing stuff on? You kind of need to trust them because they wrote the code. So if there's a bug, there's a bug. But also the benchmark directly gives you the weight, and the weight directly gives you how much you need to pay for fees. So there's no way there's a weight, but if you pay the fees that are that correspond to that weight, that it will fail. So if there's a weight, you need to pay as much for that weight as you need. Okay, you had a follow-up or?
Two related questions related to this one. First, if I set fees less than the cost needed, that will happen to my transaction. The second
will have
one,
an error, yeah.
Error even before the transaction being executed.
So the XCM, the local XCM is included yes in a transaction, and if you pay less than what you have to do locally, then it will give an error locally, and it will be reverted like every frame call. If you send less than what you need to pay remotely, it will give an error remotely, and it will be trapped in the remote chain. All the assets that are left over will be trapped in the remote chain since they won't be able to come back. Unless you put, they will be trapped in the remote chain. Yeah.
Now I have more questions.
Okay, but
I'm just imagine a scenario where it's the same point. Imagine a scenario, the destination chain put the weight is 100, which while it's the actual weight is 150. And
why do you mean the actual weight?
Because they misestimated it.
Well, if he misestimated,
in the destination chain, the other developer another parachain developer, they misestimate the weight and put the weight in the extrinsic, like this 100, and the actual cost is actually 150.
Okay, then
Because-
wait. Then it's fine. You need to pay what they said you need to pay. If their chain is dosable, because they put weight 100, but their extrinsic actually loops over 1,000,000 things, then it's their problem. Like you will not get an error when you want to pay for
But my
things.
asset will be locked.
Your asset will be locked.
Because I will I transferred my asset and it's locked in my source chain. How can I revert back this?
No, so wait. So I think there are a lot of assumptions here. So you can send a message, pay some fees. The fees might be wrongly benchmarked, like the instructions might be wrongly benchmarked, and you are sending the tokens, but the execution might still succeed. In the case of like you paying less than the cost, the execution will still succeed. It's just that you paid less than you should have in theory, but they accepted that amount of fees. Maybe they are accepting that because they just want people to use their chains, and they're kind of like subsidizing the execution. But that doesn't mean your things will. That doesn't mean it will error. It will not error if they say you need to pay 100 and you pay 100. It will not error. It will succeed. So then, if you do whatever you wanted to do, and then if you want to get those tokens back, you can just send them back. Like everything succeeds fine on that case. If you pay less than what they said you need to pay, then there is an error, and you do need to send a message back to claim them. But it doesn't, like, you don't care at this stage if their benchmarks are wrong. If their benchmarks are wrong, what it means is people can just spam them with very low fees, and then, yeah, their chain will be unusable because it will be spammed all the time. But that doesn't affect the just one message being sent, right? So if they say the weight is this and that is wrong, then you don't care. It's okay. For you, at least, right? But maybe, yeah, if they say the word benchmark is wrong, you do know there's a vulnerability on that chain. So you might be wary when using it if you know about it, right? Because if you know about it, then an attacker probably knows about it. They will probably DOS it. And then, yeah, then maybe you do send a message and they never get to it because they are being DOSed. Yeah. Okay.
Is there a way to resend a message, like Ethereum message?
Yeah, so you can definitely send it again. The thing is, you sent your funds already. So we will talk about this is all transfer protocol things again. So yeah, I know you want to know how the transfer protocol works. It doesn't do automatic retries because you send money, so you don't want to like retry and send more and more and more, and then you're left with no money, and all of it is locked on the other side. So it doesn't do automatic retries. You can like retry the message again and maybe claim what you got, what was trapped. We can talk about that later, yes. Okay, any other question? We can move on. Okay, let's move on. So we talked about the local message, or the local program, which would execute the thing. It would execute some instructions and result in a remote message being sent. And also burning, like we talked about this before. When you execute this initiate transfer, you would do the two things at the same time that Naren was saying, like you burn and you send. And all of the message is like a transaction. If any of the parts fail, you just roll back. And now let's look at the remote message. This is exactly what we saw on the previous slide. After executing the local XCM, we send the remote one, which does reserve asset deposited, pay fees, reserve asset deposited, clear origin, and deposit asset all Bob. And now let's execute that on the other side, okay? So there is some chain state, which has a Bob account. There are some registers, which are origin, holding, and fees, the same as the other example. And there's a bunch of instructions. This time, the instructions are much shorter because initial transfer takes a lot of things. So as you see, the origin is not asset hub /Alice. It could be, it very well could be, but it is Asset Hub. Why is it Asset Hub? Because we need to know that the origin is Asset Hub to allow for it to mint tokens. We cannot allow Alice to mint tokens, but we can allow Asset Hub to tell us that it moved stuff to our sovereign account. So what we do is we call reserve asset deposited. That gives us 5 dot on holding. We pay fees. This time I did it correctly. Holding is left with 4.9. Fees might be left with 0.06, for example. Then we put 10 USDT, sorry. Then we clear the origin. So origin is none. Why is origin none? Basically because these 4 instructions that are here, these 3 instructions that are at the top are basically system instructions. And then at the end, we inject user instructions. So there's sort of like a privilege zone, which is the 3 first messages. I mean, the user can specify how much goes into pay fees, but we craft it in a way where the 3 at the top are sort of privileged. Then there's a clear, and then from clear below, it's all user injected instructions. So we don't want them to act on behalf of the Asset Hub root. That would be terrible. So we clear the origin, and then all they can do from this point onward is use the assets that are in holding, right? They can now deposit assets, and boom, Bob has the amount that they want. And here, yeah, there are some leftover fees. I just leave that there so you know how that works. In reality, you would just refund it, and Bob would get, instead of 4.9, they would get 4.96. Like they would get the full amount. And that is it. But let me give an example of what might happen. Yeah, so here, this was the local XCM, okay? So in the local XCM, as we saw, the user specified this remote XCM, right? This remote message, they nested it, that only has this instruction deposit asset Bob. So if we went to the remote one, we would expect, I don't know, like only this instruction to be there. But the system injected all of this instruction that's at the top. So the system injected the reserve asset deposited, pay fees, reserve asset deposited, clear origin to make sure that everything worked correctly. Of course, this is best done, this is best understood by playing around with the executor, right? And actually going through these things. Even though we have this diagram and we're going through it bit by bit, of course, you will see it when you execute it. So we will have the exercise when you try it out, where there will be the assignment where you will test out executing things. For now, we have talked about the XCVM, which is the specification, and the XCM executor, which is the implementation of the virtual machine that grabs the instructions and it executes them one by one. And the next thing that we will talk about, which will be tomorrow, we will talk about the palette XCM, which is just an interface between Frame and XCM to tie these concepts together. We will keep on talking about the example and like where does this palette come in, right? But for now, we do have time for questions, and we'll do a little bit of code exploring, right? Some live exploring of the repository and the code, so you can get used to seeing it and looking into it and ask any questions you want about that. And then in the afternoon, we will have exercises. Okay, good. So questions, perfect. One question at the back. Yeah.
And just like I want to understand the example we have seen so far, more oriented to like parachain to parachain things. But what if I'm doing from Polkadot, any parachain, to outside Ethereum or any other like network?
Yeah, so if you go from, so I put the example up on screen. So if you wanted to send something like Asset Hub to Ethereum, for example, then the local execution would look the same because it's the same. But Ethereum doesn't do this, right? There's no, it could.
And also the cost, the fees, because like you cannot, it's not that deterministic, like to say, yeah, this amount of money, sorry, amount of gas you're
Yeah.
paying, stuff like this.
Exactly. So there could be an XCM executor or like an implementation of the XCVM on Solidity, like a smart contract that takes the bytes, scale encoded, and that's all the thing. The issue is, yeah, scale encoding. It's not like the default encoding on Solidity, and then the executor has a lot of extra things that might be too expensive in gas terms. So for example, what Snowbridge does is it grabs this remote XCM and it transforms it, like sees the intention, which is to send 5.10 USDT and deposit it to Bob. It sees the intention and it converts it into a shorter command, and it just sends the command and executes the smart contract, which will do the thing.
And I have to trust this no bridge as if like it's trusted bridge in this case.
Yeah, the word trust is we use it in various different ways, don't we? Because you trust the bridge, you trust the code, in the same way that you trust any computer program when you execute it, right? Like
Yeah, but there are some type of like trustless bridges where you have like other like kind of many entities kind of like doing the validation and the monitoring the system, making sure like no like misbehaving node like I don't have to like go to you and lock my money with you, and then I trust that you are like doing the good job.
I agree, and Snowbridge is a trustless bridge. So the caveat, I mean, there is no caveat, there is no sort of, the trade-off is that trustless bridges are more expensive than trusted bridges, like trusted multi-sig bridges. But I really wanted to make it sure, like to let you know and make sure that you guys know that Snowbridge is a trustless bridge. And for example, Hyperbridge as well. Like we really like trustless bridges. We don't like multi-sig trusted bridges. We do have them in, like, for example, Moonbeam, because people have deployed the like wormhole things and so on. But the system grabs this message and sends it over to Snowbridge, right? To the part of the code that is from Snowbridge. Snowbridge will grab this intention and convert it into a command. Of course, you need to trust that the code does what it's supposed to do. But then the command is put into a queue, and then there are off-chain relayers that would need to grab your message and post it on Ethereum, and they would post it alongside a cryptographic proof so that you know that it actually came from there. And in order to verify it, Polkadot is running an on-chain light client of Ethereum, like following Ethereum consensus to make sure that it can like have these proofs and validate everything's going smoothly. So that's I don't have like a lecture on Snowbridge because I'm also not an expert, but it is a trustless bridge, and we have like a stack that we also use on Polkadot Kusama, which is the same thing, and we do the same mechanism with cryptographic proofs and off-chain relayers that anyone can run wherever they want. And if you created a new chain and wanted to have a bridge to Polkadot, you would probably use that same stack that we have created. That it's all based in Frame, or there's a Frame part, right? There's also in Solidity, there's like a gateway contract and all of the implementation on that side. But if you wanted to create the substrate Solar chain, then you could very easily, I mean, not sure how easy it is because we made it for these bridges, and we have the task to make it more generic so that anyone can just like grab it and make a bridge to their chain, right? But yeah, so trustless bridges is the good stuff. So between parachains, we use HRMP, which kind of already uses the relay chain that we all trust, so that to make sure they send messages, so everything is fine in like parachain to parachain. If you want to send to another ecosystem or another network, trustless bridges is the way, and we have a bunch of those as well. Good. They just might not work. In order to appeal to everyone, they might not use the same executor or this XCVM. They might do other things like the thing that Snowbridge does, which I think is fair. It's just translating intentions. Yeah, question there?
So does XCM work with solo chains like A-0 or something? Can you send to solo chains and it'll work? Or would the solo chain have to like allow that or something?
Yeah, so you can send to solo chains. You would need to have a bridge, because if not, you don't know how to get there. And you might need, yeah, some configuration of like, if you want to receive USDT from Asset Hub, you might first make a bridge and then configure Aleph0, for example, to allow Asset Hub to move USDT. So basically recognize that Asset Hub is the issuer of USDT, pretty much.
I mean, I could see needing a bridge to like Ethereum or Solana, but I would think that Aleph0, since it's based on the Polkadot SDK as well, you wouldn't need a bridge for that.
Yeah, but even if it's based on the same stack, it's still a standalone chain. Like it's not a parachain. If it's a parachain, you get HRMP for free. If it's a solo chain but based on, like built on the SDK, you do get a lot of pallets that we use. Like we use a lot of pallets for this bridging thing. And because you're Polkadot SDK, you can just include the pallets and configure some things. I have never tried it, and I don't think we have like a very friendly documentation of how to do it, because not many people are launching chains, like solo chains and bridges every day. But I know if you were running on the SDK, you can just grab our pallets, and I think there is some document out there that will tell you how to configure your bridge, and then you should be able to get it to work. And then with some minor configuration, it might be needed. Yep.
So we've mentioned bridges quite a lot, and it's been on the slides a lot. Have I forgotten? Has there been a module on bridges, or
okay,
is it coming up, or have I just forgotten?
Yeah, so
about
we
it?
will not teach you about bridges in the sense that we will not teach you about how bridges work. I mean, I have said some things for people that do know how some bridges work or so on. I will not teach you how bridges work, but bridges are just a way to get from A to B. So they're the transfer protocol. So this lecture will be, or this next 3 days will be just about the application layer, like how you can actually do cross-chain interactions. You don't need to worry about whether or not you're going through HRMP, which I will also not explain how it works on a lecture, or if you're going through Snowbridge or Hyperbridge, which I will not explain how they work on a lecture. Yeah.
So could you summarize, or could we summarize that a bridge would be needed for anything outside of your trusted parachain ecosystem?
Yeah, so I think a bridge is needed all the time if you want to move from one chain to another. In Polkadot, we have like a bridge-like protocol. It's like a way to move from A to B between parachains. So because parachains like are part of Polkadot, like they do submit para blocks, and the collator and the validator have like this relationship. We can actually use the relay chain to relay messages, and that's why it was called the relay chain, to relay messages to one parachain to another. So it's kind of the relayer is the relay chain. But in regular bridges, the normal components are just chain A, chain B, and off-chain relayers. And the relayers are just programs that will grab a message from some message queue or something and post it on the other chain alongside a cryptographic proof that it actually came from the chain. That's the basic idea. And in the case of parachains, the relay chain is the relayer already, so you don't need off-chain relayers. You have an on-chain relay. Okay. Good. That's the basic idea. Yeah, I never want to make this about Snowbridge or bridges, trustless bridges in general, but I know it's a very cool topic, so I just mentioned it. But even if you use a bridge, I mean, yeah, there are some bridges that don't use XCM, like Hyperbridge doesn't use XCM, so you cannot do the same things you can do with Snowbridge. But in Snowbridge, you can use the same logic, and if you just put destination Ethereum, it will know to route it via the bridge. That's it. It will know what transport protocol to use based on your destination.